Hello, friend. Welcome. It's good to have you here tonight. Some nights the sky feels closer than it should. Stars pulse softly. Time slows in silence. And somewhere, 140 million miles away, a red light watches back. Mars, the red planet. A world that has stared at us for as long as we've had eyes to see. But lately, something has changed. Instruments are picking up signals we can't explain. Methane appears and vanishes. The ground trembles with rhythms that shouldn't exist on a dead world. Scientists whisper in conference rooms, careful with their words, because what they're seeing doesn't match what they thought they knew. Mars is not sleeping. Mars is listening, and perhaps it's trying to tell us something we're not ready to hear. Before we begin this quiet journey together, if you find comfort in these stories, told softly, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more nights like this, and ring the little bell, not for noise, but so the next quiet discovery can find you again. These small gestures help this space grow, and I'm grateful you're here. Now, let's drift. Tonight we're traveling to a world that has haunted human imagination longer than recorded history. A world that glows red in our night sky like a distant ember. A world we've named after gods of war, death and mystery. Mars. But this isn't a story about conquest or colonization. This is something quieter. This is about recognition. About the moment when a species looks up at a point of light and realizes for the first time that it might be looking at a mirror. You don't need to understand everything. Just rest and let curiosity do the listening. There's a particular quality to Martian light that ancient peoples noticed immediately. It doesn't twinkle like other stars. It holds steady burning, with a color that seems almost alive, rusty, blood-warm, patient. While other celestial objects danced and flickered, Mars simply watched. This steadiness, this unwavering presence made it different, made it important, made it feel somehow aware. The earliest records we have come from Babylon around 1600 BCE. Astronomers there tracking the heavens with remarkable precision called Mars Nergal, their god of plague war and the underworld. They noticed that when Mars appeared brightest, when its ruddy glow dominated the pre-dawn sky, kingdoms often fell. Empires collapsed. Fever swept through cities like invisible fire. Perhaps it was coincidence. Perhaps it was pattern recognition gone wrong, seeing cause where there was only correlation. But they watched and they recorded, and they believed the Red Wanderer carried messages written in light. The Egyptians saw it differently. They called Mars Har Desher, meaning the Red One, but their interpretation was more complex. Mars moved backwards, sometimes retracing its path through the constellations, what we now call retrograde motion. And this reversal fascinated them. A star that changed its mind. A light that remembered where it had been and chose to return. In their cosmology, this wasn't threatening. It was philosophical. The universe they understood did not move in simple straight lines. Even the heavens practiced reflection. Chinese astronomers named it Yinghuo, the Fire Star, and tracked its movements for over 3,000 years with obsessive detail. They didn't assign it qualities of war particularly. Instead, they saw Mars as an indicator of imbalance. When it appeared in unexpected positions, it suggested disorder in the relationship between heaven and earth ruler and ruled nature and civilization. Their records are so precise that modern astronomers still use them to calculate ancient Martian orbits, checking our computer models against observations made with nothing but patient eyes and careful notation. The ancient Greeks inherited these observations and wove them into their pantheon. They called the planet Ares, after their god of war, not the noble strategic war of Athena, but the chaotic, bloodthirsty violence of battlefields. Ares was not loved even by other gods. He represented the worst impulses of human conflict. And there in the night sky was his star, blood-colored and relentless, a reminder that destruction was always present, always waiting. When Rome absorbed Greek astronomy, they softened the name but kept the association. Mars their own god of war, but also of agriculture, of spring, of the protection of the Roman people. the planet became woven into their civic identity. The month of March, when the campaigning season began, was named for Mars. The Campus Martius, where armies trained, honored Mars. Roman generals would read the position of the planet before major battles, looking for favorable signs in its brightness. Its height above the horizon, its position relative to other wandering stars. But here's what strikes me as remarkable across all these cultures separated by thousands of miles and hundreds of years. The interpretation was consistent. Mars meant change. Mars meant transformation. Mars meant the end of one thing and the violent beginning of another. Different languages, different mythologies, different philosophies, but the same red light, producing the same sense of unease, the same association with forces beyond human control. Was this purely superstition? Probably yes. The planet's color comes from iron oxide rust, essentially covering most of its surface. Mars is red for the same reason blood is red, the same reason old metal left in rain turns red. Iron meeting oxygen. Chemistry, not destiny. Though ancient observers couldn't have known this, they saw color and assigned meaning the way humans always do when confronted with phenomena we can't explain. But perhaps they were noticing something real, even if they misunderstood what it was. Mars does affect Earth, just not in the ways they imagined. Its gravity, while small, contributes to the complex gravitational dance that stabilizes Earth's orbit. Its presence in our solar system affects the distribution of asteroids, the trajectories of comets, the long-term stability of the inner planets. Remove Mars and Earth's climate would eventually spiral into chaos, swinging between extremes that would make life impossible. In a very real sense, Mars protects us. The god of war standing guard. The Maya, half a world away from Mediterranean civilizations, came to similar conclusions independently. They tracked Mars with extraordinary accuracy, noting its 780-day synodic period, the time it takes to return to the same position relative to Earth and Sun. They wove this cycle into their calendar systems, their agricultural predictions, their sense of cosmic order. When Spanish conquistadors arrived and shared European astronomical knowledge, Mayan scholars were unimpressed. They had already figured it out centuries earlier, using stone observatories and generations of patient watching. What were all these ancient peoples doing, really, when they watched Mars? They were practicing the first form of planetary science. They were asking, what is this thing? Why does it move the way it moves? What can it tell us about the structure of reality? They didn't have telescopes. They didn't have spectrometers or rovers or orbital satellites. They had curiosity and time, and the belief that understanding the heavens meant understanding ourselves. They were wrong about many details. Mars didn't cause wars or plagues. Its color didn't carry divine messages. The gods they associated with it were human inventions, projections of our fears and fascinations onto points of light we couldn't reach. But they were right about the essential thing: Mars mattered. Mars was worth watching. Mars had something to teach us if we paid attention long enough. And here's the whisper underneath all of this. They were looking at a world that had died. The Mars. They observed the Mars that glowed steady in their night skies was already a corpse. Its oceans had evaporated billions of years before the first human eyes evolved. Its atmosphere had been stripped away by solar wind, leaving a thin ghost barely thick enough to carry dust storms. The magnetic field that once protected it had collapsed. By the time anyone looked up and named it after gods, Mars had been silent for eons. But they didn't know that. They thought they were looking at something eternal, unchanging, a fixed point in the cosmic order. They thought the red light would burn forever, steady and watchful. They couldn't imagine that worlds could die, that planets could transform from living, breathing places with rivers and rain into frozen deserts where nothing moved but dust. They believed the universe was stable, permanent, safe. We know better now. We've seen the images read, the data, understood the story Mars tells in its geology. But knowing doesn't make it less haunting. If anything, it makes the ancient observations more poignant. All those civilizations watching a dead world and calling it a god. All those careful records tracking the orbit of a planet that had already lost everything that made it alive. They were performing a vigil without knowing it, keeping watch over a tomb they thought was a temple, and maybe in a way we're only beginning to understand they were picking up on something true. Because Mars isn't quite finished, deep below that rusty surface, processes continue. Water ice still exists, locked in polar caps and buried lakes. The planet's core still radiates heat, slowly cooling, but not yet cold. Seasonal changes still occur. Carbon dioxide freezes and thaws, pressure shifts, dust moves in patterns that almost look deliberate. Mars is not alive, but it's not entirely dead either. It exists in some liminal state between neither one thing nor the other, suspended in a transformation that takes billions of years to complete. The ancients saw a steady light and called it eternal. We see a dying world and call it dead. Maybe both observations are too simple. Maybe Mars is teaching us that endings are slower than we imagine, that death is not an instant, but a process that even worlds take their time letting go. So, when those Babylonian astronomers looked up and saw Nergal burning red, when Chinese scholars tracked Yinghuo through its retrograde loops, when Roman generals read omens in the height of Mars above the horizon, what were they really seeing? They were seeing themselves. Human consciousness reflected in a point of light. The part of us that knows transformation is real, that change is constant, that nothing lasts forever, but some things last longer than we can imagine. They were practicing the first tentative steps of a conversation that would take 4,000 years to begin in earnest. Because we're still watching. We've never stopped. We've just gotten better tools, ask more precise questions, travel closer to the answers. But the impulse is the same: look up, wonder what that red light means, and try to understand what it's telling us about the universe, about ourselves, about the thin line between living and dying that all worlds eventually walk. Mars has been patient. It waited while we invented writing, mathematics, the scientific method, rocket engines, computers. It waited while we figured out how to leave our own planet, how to build machines that could survive in vacuum, how to listen to signals traveling across millions of miles of nothing. It waited steady and read the same patient light that ancient eyes saw, carrying the same mysteries they couldn't answer. And now, we're ready to listen. Now, we have the instruments sensitive enough to detect methane molecules in Martian air. Now we have seismometers that can feel Marsquakes rippling through ancient bedrock. Now we have radar that can see lakes hidden beneath polar ice. Now we're hearing things that don't make sense, that challenge what we thought we understood about dead worlds and silence and endings. Mars is still speaking. It never stopped. We're just finally learning the language. The ancients were right about one thing. Mars is a messenger, not of war or plague or divine will, but of something more profound. It's showing us what happens when a planet loses its protection, its atmosphere, its water. It's demonstrating what Earth could become, given enough time and the wrong conditions. It's a warning, written in geology, in atmospheric chemistry, in the ghost traces of rivers that stopped flowing before life on Earth had evolved past single cells. But warnings can also be invitations. If we can read what Mars is telling us about climate change, about planetary magnetic fields, about the fragile conditions that allow life to persist, then maybe we can avoid the same fate. Maybe the red light our ancestors feared isn't a threat. Maybe it's a teacher. Maybe it's been trying to save us all along if we could just learn to understand what it's been saying night after night for billions of years. The ancient sky watchers noticed something we're still grappling with. Mars doesn't behave like other celestial objects. It moves with intention, loops back on itself, changes brightness in patterns that seem almost deliberate. Of course we know now, it's just orbital mechanics, the mathematics of two planets circling the same star at different speeds, creating apparent reversals and variations in distance. But the feeling remains, the sense that Mars is doing something, not just being something, that it's active, not passive, that it's watching us as much as we watch it. And perhaps that feeling, that ancient intuition, is closer to truth than we realized. Because Mars is active, it's transforming, it's processing, deep in its subsurface in pockets of brine that remain liquid despite the cold, in mineral reactions that release trace gases in the slow decay of radioactive elements that still warm its core. Mars continues. It persists. It refuses to be completely still. We're about to discover just how unstill it really is, just how much activity hides beneath that rusty silence, just how wrong we were to call it dead. But first we need to understand what those ancient observers began the practice of watching, of recording, of asking what the Red Wanderer wants us to know. They started a conversation 4,000 years ago, using nothing but their eyes and their curiosity. We're continuing it now with rovers and orbiters, and instruments sensitive enough to detect single molecules floating in thin Martian air. The questions remain the same. The answers are just beginning to emerge, and they're stranger, more beautiful, more unsettling than anyone ancient or modern could have predicted. Something is happening on Mars, something that challenges everything we thought we understood about lifeless worlds and cosmic silence. The instruments are picking it up, the data doesn't lie, and the Red Planet patient, as always, is finally ready to show us what it's been hiding all this time, waiting for us to develop ears capable of hearing what it's been whispering across the darkness, generation after generation, a message we're only now beginning to decode. The first person to truly see Mars wasn't an astronomer. They were simply someone who looked up one evening and noticed something odd, a red star that didn't behave like the others. A light that moved with purpose through the fixed constellations, tracing patterns that repeated but never quite the same way twice. We don't know their name. We don't know what language they spoke or what they thought when they first recognized the pattern. But in that moment of recognition, something shifted. Humanity stopped being passive observers of the night sky and became detectives trying to solve a mystery written in light. The oldest confirmed astronomical record of Mars comes from a clay tablet found in Babylon, dated to approximately 1534 BCE. The tablet is small, barely larger than a human hand, covered in cuneiform script, so precise it required a magnifying glass to read properly when archaeologists first examined it. The text describes Mars's position relative to certain stars in what we now call the constellation Scorpius. But it's not just an observation, it's a prediction. The scribe who wrote it was calculating where Mars would be in the future based on where it had been in the past. They understood 35 centuries ago that the Red Wanderer followed rules. Invisible rules, perhaps divine rules, but rules nonetheless. This wasn't mysticism. This was the birth of planetary science written in wet clay with a reed stylus preserved by accident. When the building it was stored in burned down, baking the tablet hard enough to survive millennia, the Babylonians didn't have telescopes, didn't have computers, didn't have calculus or physics or any of the mathematical tools we consider essential for understanding celestial mechanics. What they had was patience. They watched Mars for generations, passing down observations from teacher to student, building a database of positions and dates that spanned centuries. They noticed that Mars appeared brightest at certain intervals, what we now call opposition, when Earth passes between Mars and the Sun, bringing the two planets closest together. They noticed the retrograde motion, when Mars seemed to reverse direction against the background stars. They couldn't explain why these things happened, but they could predict when they would happen again. And prediction, not explanation, was the goal. If you could predict where Mars would be, you could read the future in its movements, or so they believed. But here's what makes their observations so remarkable: they were right. Not about Mars causing plagues or wars, but about its behavior being predictable, mathematical, lawful. When modern astronomers fed those ancient Babylonian observations into computer simulations of the solar system, they matched. The tablet from 1534 BCE described Mars in a position that our best orbital mechanics software confirms it actually occupied on that specific date. Across 3,500 years, the numbers aligned. Those scribes working with nothing but their eyes and the belief that patterns mattered had achieved genuine astronomical accuracy. They had touched something real. Move forward 1,000 years to ancient China during the Warring States period around 400 BCE. Chinese astronomers developed their own system for tracking Mars completely independent of Babylonian methods. They called it Yinghuo, the Fire Star, and they were obsessed with its brightness variations. They created a scale 5 distinct levels of luminosity and recorded which level Mars displayed on specific dates. Why did brightness matter so much? Because in Chinese cosmology, the intensity of celestial objects reflected the balance of yin and yang, the flow of qi through the universe. A dimmer Mars suggested weakness in yang energy, which correlated in their worldview with military defeats, poor harvests, or the decline of imperial authority. A brighter Mars meant yang energy was ascending, often interpreted as a time for decisive action, military campaigns, or major policy changes. Were they reading Mars, or were they reading themselves? Perhaps both. The human mind is extraordinarily good at finding patterns, even patterns that don't exist. But Mars does actually vary in brightness in predictable ways, based on its distance from Earth and the angle of sunlight hitting its surface. The Chinese astronomers were measuring something real, even if their interpretation of what it meant was filtered through cultural assumptions. They were doing science observation and measurement record-keeping pattern recognition, but wrapping it in a philosophical framework that made sense to them. And their records are so detailed, so consistent across dynasties, that modern researchers use them to refine our understanding of how Earth's and Mars's orbits have subtly shifted over the past 2 millennia. Ancient Chinese observations made for mystical purposes now serve as data points in gravitational calculations. The universe has a sense of irony. The ancient Egyptians approached Mars differently. They were less concerned with prediction and more interested in what Mars's movements revealed about the structure of the cosmos. Egyptian astronomers noticed that Mars, along with several other wandering stars, moved against the background of fixed constellations in a specific band, what we now call the ecliptic, the plane of the solar system. They understood intuitively that these wanderers were different from ordinary stars. They occupied a middle ground between Earth and the distant, unchanging lights. This 3-tiered cosmos, Earth below, wandering stars in the middle, fixed stars above, was their model of reality. And Mars, blood red and restless, was one of the key pieces of evidence that the universe had layers, that reality was more complex than simple observation suggested. Egyptian priests tracked Mars for ritual purposes, timing certain ceremonies to coincide with its appearances and disappearances. But they also tracked it out of pure curiosity. Temple walls at Dendera, dating to the Ptolemaic period, include astronomical ceiling paintings that show Mars in specific positions relative to other planets and constellations. These aren't functional calendars or religious texts. They're astronomical maps created by people who wanted to understand the architecture of the heavens. They were asking, what is the shape of space? How do these lights relate to each other? What laws govern their movements? The answers they found were wrong in details but right in spirit. The universe is orderly. The wandering stars follow paths. Mars is not random. These insights carved in stone represent humanity's first attempts at cosmology, the science of the universe as a whole. Then came the Greeks, and everything changed. Around 350 BCE, a philosopher named Eudoxus of Cnidus proposed a radical idea: the wandering stars, including Mars, were attached to invisible spheres that rotated around Earth at different speeds. This wasn't mysticism. This was a mechanical model, an attempt to explain retrograde motion and brightness variations using geometry. It was wrong. Mars isn't attached to a crystal sphere, but it was the right kind of wrong. It was a testable hypothesis, a mathematical framework that made predictions. When the predictions didn't match observations perfectly, later astronomers like Callippus and Aristotle added more spheres, making the model more complex to improve its accuracy. They were doing science. Not modern science, not with our tools or methods, but the fundamental process: observe, hypothesize, test, refine. They were taking Mars seriously as a problem to be solved, not just a god to be worshipped. Aristotle himself wrote extensively about Mars in his work, On the Heavens. He noticed that Mars appeared redder than any other wandering star, and he theorized that this color came from the planet being composed primarily of fire. Close in a way, iron oxide does involve oxygen, which is essential for combustion. Aristotle couldn't have known about chemical oxidation, but he was grasping at a material explanation for a physical property. He was asking the right question: why is Mars red? The answer he gave was wrong, but the act of asking, of refusing to accept, because the gods made it so, as sufficient explanation, was revolutionary. It opened the door for every astronomical discovery that followed. Hipparchus, around 150 BCE, took things further. He compiled a star catalog, the first comprehensive map of the night sky, and he noticed something peculiar when comparing his observations to those made by earlier astronomers. The positions of the stars were shifting slowly over time, rotating around a fixed point. He'd discovered the precession of the equinoxes, the 26,000-year wobble in Earth's axis. But in the process, he also refined measurements of Mars's position with unprecedented precision. He could locate Mars to within a fraction of a degree, using nothing but a simple angle measuring device called a dioptra. His work allowed him to calculate that Mars's orbit took approximately 687 days. Not Earth days, but the time it took Mars to return to the same position relative to the background stars. The actual number is 687 Earth days. Hipparchus, using Bronze Age technology, got it exactly right. Ptolemy, building on Hipparchus's work around 150 CE, created the most sophisticated model of Mars's motion that the ancient world would produce. His Almagest described Mars's path using epicycles, circles, moving on circles, a geometrically complex but mathematically elegant solution to the retrograde problem. The model was geocentric, placing Earth at the center, which we now know is incorrect, but it worked. It predicted Mars's position with remarkable accuracy for over 1,000 years. Medieval Islamic astronomers used Ptolemy's tables, as did European navigators, as did early Renaissance scholars. A wrong model that made correct predictions, what does that tell us about the nature of science? That accuracy and truth aren't always the same thing. That sometimes a beautiful lie reveals more than an ugly fact. That Mars has always been generous with its mysteries, allowing multiple interpretations, multiple approaches, multiple ways of being understood. The ancient Maya, half a world away from Mediterranean civilization, were watching Mars with equal intensity. In the Dresden Codex, one of only 4 surviving Maya books, there's a section called the Mars Table, 8 pages of hieroglyphs, tracking Mars's synodic period, the 780-day cycle, from one opposition to the next. The Maya calculated this period as 780 days. The actual period is 779.94 days. They were off by 0.006%. Using naked eye observations from stone pyramids without any optical instruments, they achieved accuracy that wouldn't be improved upon until the invention of the telescope. How? The same way the Babylonians did it: time and patience. Mayan astronomers watched Mars for centuries, recording every appearance, every position, every brightness variation, compiling data across generations until the pattern emerged with crystal clarity. But the Maya interpreted this data through their own cultural lens. They associated Mars with their god, Kukulkan, the feathered serpent, and believed that Mars's movements reflected agricultural cycles. When Mars rose before dawn, it signaled time for planting certain crops. When it set after dusk, time for harvesting. Were they right? Partially. Mars's position does correlate with Earth's seasonal cycle because both planets orbit the same sun. The Maya were noticing a real relationship, but attributing it to divine will rather than gravitational mechanics. They were seeing the connection between Earth and Mars, understanding that what happened up there related to what happened down here, but lacking the framework to explain why. Still, their observations were so precise that modern archaeoastronomers use Maya calculations to verify computer models of ancient planetary positions. The same dance of mathematics, different language to describe the steps. What strikes me most about all these ancient observations isn't their accuracy, though. That's impressive enough. It's their universality. Every culture that watched the sky for more than a few generations eventually focused on Mars, not Venus, which is brighter, not Jupiter, which is larger and more prominent. Mars. Why? Perhaps because Mars is the most obviously dynamic. It changes brightness dramatically. It reverses course visibly. It appears and disappears with irregular timing. It demands attention in a way that other planets don't. It's the squeaky wheel of the solar system, the one that refuses to be ignored, the one that seems to be doing something rather than just existing. Or perhaps humans gravitated toward Mars because on some unconscious level, we recognized kinship. Mars is rocky like Earth. It has seasons like Earth. It has polar caps like Earth. It has day lengths almost identical to Earth, 24 hours and 37 minutes. From a distance without telescopes, ancient observers couldn't have known any of this. But maybe they sensed it anyway. Maybe the reason every culture that studied Mars associated it with life-death transformation and rebirth is because Mars actually is transforming. It's dying slowly, and its death is visible to anyone who watches long enough, who pays attention to the subtle shifts in color and brightness that mark atmospheric changes, dust storms, seasonal cycles. The ancients were watching a world bleed out across geological time, and they called it a god because they didn't have vocabulary for planetary death. Here's a question worth sitting with. What did those first observers feel when they realized Mars moved against the background stars? Not what did they think we have their writings for, that their theories and calculations and mythologies, but what did they feel? That moment when the pattern clicked, when the chaos resolved into order, when the red light stopped being a mystery and became a puzzle with rules, with structure, with predictable behavior. Was it triumph, relief, or was there disappointment, a sense that solving the mystery diminished the magic we'll never know? But I suspect they felt what every astronomer feels when the data finally makes sense, a mixture of satisfaction and melancholy. Satisfaction that the universe is knowable. Melancholy that knowing it makes it smaller, somehow less wild, less free. The ancient skywatchers gave us more than data. They gave us a methodology. Watch, record, compare, predict, test, refine. They established that Mars was worth studying not because it affected human affairs, it doesn't, but because it revealed something about the structure of reality. They created the first astronomical databases, the first mathematical models of planetary motion, the first systematic attempts to understand the cosmos through observation rather than revelation. They weren't always right. Their theories were often wildly incorrect, but their approach was sound, and their data painstakingly collected over centuries provided the foundation for every astronomical discovery that followed. When Copernicus placed the sun at the center of the solar system in 1543, he was building on Ptolemy's observations of Mars. When Kepler discovered that planets move in ellipses rather than circles, he was analyzing Tycho Brahe's meticulous measurements of Mars's position over decades. When Newton formulated the laws of gravity, he tested them against centuries of accumulated data on Mars's orbit. Every revolution in astronomical understanding depended on information compiled by people who never saw through a telescope, who never left Earth's surface, who had only their eyes and their persistence and their belief that the Red Wanderer's movements meant something. They were right. They just didn't live long enough to learn what. Standing at this threshold between ancient observation and modern understanding, we can see how far the conversation has come. From clay tablets recording Mars's position in Scorpius to spacecraft landing on Martian soil, the lineage is direct. We're still doing what the Babylonians did, watching, recording, trying to understand what the red light means. We have better tools now, instruments that can detect molecules and measure magnetic fields and listen to seismic waves traveling through alien rock. But the impulse is identical. Look at Mars. Pay attention. Ask what it's trying to tell us. And Mars, patient as always, continues speaking in the only language planets know, evidence written in chemistry and geology and the slow transformations of deep time. The ancients heard part of the message. They understood that Mars mattered, that its movements reflected something true about the cosmos, that studying it was worthwhile. They couldn't have imagined what we'd eventually discover: the dead oceans, the lost atmosphere, the possibility of ancient life. But they knew enough to keep watching. They knew enough to pass the work to the next generation, trusting that eventually someone would decode what Mars has been saying all along. That moment is arriving now. The instruments are sensitive enough. The data is comprehensive enough. The questions have been refined over 4,000 years of continuous observation. Mars is ready to reveal what it's been hiding. And the story it tells is stranger than any ancient myth, more beautiful than any god tale, more urgent than any prophecy. Because Mars isn't just speaking to us about itself. It's speaking to us about Earth, about what we could become, about the thin margin between life and silence that every world eventually faces. The ancient observers started the conversation. We're about to hear the answer. Sometimes the most dangerous thing in science isn't ignorance, it's certainty. In 1877, an Italian astronomer looked through his telescope and saw lines on Mars, straight lines, geometric lines. Lines that crossed and connected like a vast network of highways or waterways. He called them canali, a word that means channels in Italian, but was translated into English as canals. And with that mistranslation, with that single word, carrying the weight of intentionality, of engineering, of civilization, humanity convinced itself that Mars was not just alive, but inhabited. For 50 years, some of the brightest minds in astronomy staked their reputations on the existence of Martian canals. They drew maps, they published papers, they gave lectures to packed auditoriums. They were brilliant, dedicated, and completely wrong. This is the story of how desperately we wanted Mars to be like us, and how that desperation made us see things that were never there. Giovanni Schiaparelli was not a careless observer. Born in 1835, he was one of the most respected astronomers in Europe, director of the Brera Observatory in Milan, known for his meticulous planetary observations and his discovery that meteor showers were associated with comet debris. When he turned his telescope toward Mars during the favorable opposition of 1877, when Mars came unusually close to Earth, he brought decades of experience and a reputation for accuracy. His instrument was not the most powerful available, but it was well crafted and his eyesight was excellent. He spent hours each clear night sketching what he saw on the Martian surface, building up a detailed map over weeks of observation. And he saw lines, lots of lines, dark, relatively straight features connecting darker patches he interpreted as seas. He labeled them with names from classical mythology and geography: Indus, Ganges, Nilus, Phaison. He called them canali, meaning natural channels, or grooves implying nothing more than waterways shaped by natural processes like river valleys on Earth. He published his observations in Italian astronomical journals. They were received with interest, but not excitement. Natural channels on another planet, interesting, worth investigating further, but not revolutionary. And then the word jumped languages, and everything changed. In English, canali became canals. And canals in the late 19th century meant one thing: engineering. The Suez Canal had opened in 1869. The Panama Canal was under construction. canals were humanity's triumph over geography, proof of civilization's power to reshape nature for practical purposes. If Mars had canals, it didn't just have water. It had engineers. It had civilization. It had intelligence comparable to human intelligence, facing similar challenges, developing similar solutions. The implication was staggering. We were not alone. And the proof was right there, visible through telescopes drawn on maps documented by a respected astronomer. The idea spread like fever through both scientific and popular circles. Mars wasn't a dead rock. Mars was a world, a place, perhaps even a home for beings not unlike ourselves. Enter Percival Lowell. Born in 1855 to a wealthy Boston family, Lowell had the resources to pursue any interest that captured his imagination. He was intelligent, charismatic, well-connected, and utterly convinced that Mars was inhabited by an advanced but desperate civilization. In 1894, he built his own observatory in Flagstaff, Arizona, specifically to study Mars. The location was chosen for its high altitude and clear skies, far from city lights and atmospheric turbulence. Lowell spared no expense on equipment, hiring skilled assistants and acquiring some of the finest telescopes available. And then he looked at Mars and he saw what he expected to see. Not just lines, but networks. Not just canals, but a global irrigation system. He saw a dying world where an advanced civilization was fighting for survival, channeling water from polar ice caps to equatorial deserts, building continent-spanning infrastructure to sustain life on an increasingly arid planet. He saw Mars as a mirror of Earth's potential future, what we might become if we didn't manage our resources wisely. And he dedicated the rest of his life to documenting what he believed was there. Lowell wasn't stupid. He wasn't hallucinating. He was a trained mathematician skilled in calculation and geometry. He wrote 3 books about Mars, each one more detailed than the last, filled with observations, sketches, and theories. Mars in 1895, Mars and its canals in 1906, Mars as the abode of life in 1908. The books were bestsellers. They were reviewed in major newspapers. They influenced science fiction writers, inspired artists, captured public imagination in a way few astronomical discoveries had before or since. H.G. Wells's The War of the Worlds was published in 1898, just a few years after Lowell's first Mars book, and its vision of advanced Martians invading Earth drew directly from the canal theory. Edgar Rice Burroughs' Barsoom series, beginning with A Princess of Mars in 1912, imagined a Mars of dying seas and ancient canal cities. Lowell had created almost single-handedly the cultural image of Mars that would dominate for decades a tragic world, ancient and sophisticated, struggling against inevitable decline. But here's what makes Lowell's story so psychologically fascinating. He was seeing something real, just not what he thought he was seeing. When you look at Mars through a telescope, even a good one, the image shimmers and blurs due to Earth's atmosphere. The human eye and brain, confronted with this uncertain, wavering image, try to make sense of it by connecting features, creating continuity, where there might only be disconnected patches of darker terrain. Lowell's canals were pareidolia, the same psychological phenomenon that makes us see faces in clouds or hear voices in white noise. The dark patches on Mars were real. The human tendency to connect them into patterns was real. But the canals themselves were an artifact of perception, not actual features on the Martian surface. Lowell's mind, primed with the expectation of finding geometric patterns, obligingly produced them from ambiguous visual information. He was being betrayed by the very cognitive processes that make humans such effective pattern recognizers in other contexts. Other astronomers tried to replicate Lowell's observations. Some succeeded, drawing similar maps with similar canal networks. Others failed completely, seeing only vague shadings and disconnected dark regions with no geometric organization. This should have been a warning. If the canals were real physical features, everyone with a comparable telescope should see them consistently. But that's not what happened. Whether an observer saw canals correlated strongly with whether they expected to see canals. Astronomers who approached Mars with no preconception tended to report irregular, organic-looking dark regions. Astronomers who'd seen Lowell's drawings first tended to confirm his observations. This is confirmation bias in its purest form, not a conscious decision to lie, but an unconscious shaping of perception by expectation. The observers were reporting honestly what they saw, but what they saw was influenced by what they believed they should see. The debate became increasingly polarized. Lowell and his supporters insisted the canals were real, backed by hundreds of detailed drawings made over years of observation. Skeptics argued that the canals were optical illusions, but struggled to explain why multiple observers at different locations saw similar patterns. The controversy generated papers, lectures, public debates. Lowell gave interviews to newspapers explaining his theory that Mars was inhabited by a civilization far older than humanity, perhaps millions of years more, advanced, facing ecological catastrophe as their world dried out. He suggested the canal network was visible from Earth because it wasn't just the canals themselves, but vegetation growing along the canals, creating wide bands of darker terrain, visible even at interplanetary distances. It was an elegant theory. It accounted for the observations. It explained why the dark bands were so wide, not because the canals were impossibly huge, but because they supported ecosystems along their length. The only problem was that none of it was true. The turning point came with advances in photography. Early attempts to photograph Mars through telescopes failed to show canals, but photographic technology in the early 1900s wasn't very sensitive and exposure times were long. Lowell and his supporters argued that photographs missed the canals because they couldn't capture the detail visible to the trained human eye under moments of perfect atmospheric stability. But as photographic techniques improved through the 1920s and 30s, better images of Mars revealed a surface that looked nothing like Lowell's drawings. No straight lines, no geometric networks, just irregular light and dark regions, craters, and what appeared to be dust patterns. The canals, if they existed at all, were far too subtle to show up on photographs, which seemed increasingly unlikely. By the 1940s, most professional astronomers had abandoned the canal hypothesis. They weren't on Mars. They'd never been on Mars. They'd been in human eyes and human minds painted onto ambiguous visual data by the desire to find what we'd hoped was there. But why did this matter so much? Why did intelligent people cling to the canal theory long after evidence turned against it? Because the alternative was depressing. A Mars without canals was just a dead desert, another lifeless rock in space offering nothing but geological curiosity. A Mars with canals was a populated world, a cosmic neighbor proof that life and intelligence could arise elsewhere in the universe. It meant we weren't alone. It meant the cosmos had meaning, purpose, story. Accepting that the canals were illusions meant accepting that Mars offered no easy answers to humanity's deepest questions about our place in the universe. It meant confronting the possibility that Earth might be special, that life might be rare, that intelligence might be isolated by vast distances and enormous timescales. For many, that possibility was harder to accept than the slim chance that millions of people were systematically misinterpreting telescope observations. Lowell himself never abandoned his belief in the canals. He died in 1916 still convinced that Mars was inhabited, still drawing maps of the canal network, still arguing with skeptics who questioned his observations. His observatory continued Mars research after his death, but gradually shifted focus, eventually contributing to the discovery of Pluto in 1930, a genuine astronomical achievement that vindicated Lowell's broader vision of careful, systematic planetary observation, even as it moved on from his Martian obsession. But the cultural damage, if we can call it that, lingered. An entire generation grew up believing that Mars had canals, that it was inhabited by an ancient civilization, that someday we might communicate with or visit our Martian neighbors. When spacecraft finally reached Mars in the 1960s and sent back images of a cratered canal-less desert, the disappointment was profound. Mars wasn't like us. Mars wasn't trying to survive through engineering prowess. Mars was just dead. Or so it seemed at the time. What can we learn from the Canal affair? First, that wanting something to be true doesn't make it true, no matter how sophisticated the reasoning supporting it. Lowell built an entire theoretical framework around the canals, climate science, hydrology, even xenobiology, all logically consistent, all carefully argued, all based on features that didn't exist. Second, that perception is not objective recording, but active interpretation. When we look at anything, especially something ambiguous at the edge of our perceptual ability, we're not passively receiving information. We're actively constructing an interpretation based on expectations, prior knowledge, and unconscious assumptions. The canals weren't in the telescope data. They were in the gap between data and perception filled in by minds desperate for Mars to be meaningful. Third, that scientific communities can maintain false beliefs for decades if those beliefs are emotionally satisfying and not immediately testable. The canal theory persisted because Mars was far away. Observations were difficult, and the hypothesis couldn't be definitively disproven without technology that didn't yet exist. It was unfalsifiable within the limitations of ground-based telescope observation, which gave it room to survive long after it should have died. But here's the part that makes me wonder. Were Lowell and Schiaparelli entirely wrong? Not about the canals themselves, obviously. Those definitely don't exist. But about the core intuition that Mars was trying to tell us something about water, about climate, about the struggle to sustain life on a dying world. Because that intuition was correct. Mars did have water. Mars did have a climate crisis. Mars did face exactly the kind of ecological catastrophe that Lowell imagined just billions of years earlier than he thought. The dark regions he saw weren't vegetation along canals, but they were shaped by water, ancient river valleys, dried lake beds, mineral deposits left by evaporating seas. The story Lowell told was true. He just got the timeline completely wrong. He was seeing ghosts of water systems that had died long before human eyes evolved to see anything. There's something almost tragic about how close he came to being right, while being utterly wrong in detail. Imagine if Lowell could see the images we have now, from orbital satellites and rovers, the undeniable evidence of ancient river networks, catastrophic floods, vast ocean basins. He'd recognize the landscape. It would match his intuition that Mars was a world shaped by water, struggling with water loss. He'd just have to accept that the struggle was over, eons ago, that the engineers he imagined never existed, that the canals he saw were artifacts of his own longing for cosmic companionship. Would that knowledge satisfy him, or would it feel like winning an argument but losing the prize? The canal affair teaches us something about the nature of scientific error. Most mistakes in science are boring, arithmetic errors, contaminated samples, equipment malfunctions. But some mistakes are revealing. They expose the deep structure of human cognition, the ways we fool ourselves, the price we pay for consciousness that's always interpreting, always trying to find meaning, always constructing narratives from raw sensation. Lowell's mistake wasn't carelessness. It was caring too much, wanting too badly for the data to mean something profound. It was the mistake of someone who looked at a red light in the sky and saw not just a planet, but a parable, a warning, a mirror. He was doing what humans do best and worst, telling stories about things we can barely see, using those stories to give structure to existence, believing the stories so deeply that they become more real than reality. And maybe that's why the canal myth, even after being thoroughly debunked, never quite died. It still appears in documentaries as a cautionary tale. It still shows up in discussions of confirmation, bias, and the importance of objective measurement. It still haunts conversations about Mars, a reminder that the planet we study is always to some degree the planet we want Mars to be. We've learned to be more careful. We've developed better tools. We've built scientific methods specifically designed to catch errors like this before they spread. But the impulse remains. We still want Mars to surprise us. We still hope that the next rover will find something that changes everything. We still dream of water, of life, of intelligence, of answers to the question, are we alone? The canals aren't there, but the longing that created them, that's as real as bedrock. And in a strange way, that longing has driven us to actually reach Mars, to walk robots across its surface, to analyze its chemistry, to listen to its winds, to finally get close enough to see what's really there, instead of what we wish was there. Lowell's fantasy of Martian civilization motivated a century of Mars research that eventually revealed the truth. His error, pursued with enough dedication, became a strange kind of success. We went to Mars because we believed it had canals. We stayed when we learned it didn't, because by then we discovered that the real Mars, the dead ocean, Mars, the lost atmosphere, Mars, the ancient possibly living Mars, was more interesting than any canal network could ever be. What would Lowell see if he could look through modern instruments, not lines, but stories? But stories written in isotope ratios and mineral compositions. Stories of a magnetic field that failed an atmosphere that fled a hydrological cycle that froze. Stories of a planet that was for a brief moment in cosmic time, almost like Earth. Almost. The canals he drew were wrong, but the water they represented was real. The civilization he imagined was fiction, but the tragedy he intuited was fact. Mars did die. Mars is dying still slowly over time scales that make human history look like a single breath. And we're here now, witnesses to the aftermath, trying to read what happened from the evidence left behind. The canals were never there, but the network of ancient waterways they were mistaken for, that's real, and it's written across Mars's face in a language we're only now learning to read. Lowell was looking at a corpse and seeing a patient. We've learned to tell the difference, but we're still asking the same question he asked, what happened to you, Oz? And the answer, slowly, carefully, is finally starting to arrive. There's a particular kind of silence that comes when you're waiting for a signal from another world. Not the comfortable silence of a quiet room, but the silence of distance of light minutes, stretching across emptiness of machines, falling toward alien ground, with no one there to catch them. On July 20th, 1976, engineers at NASA's Jet Propulsion Laboratory sat in a room full of computers and monitors waiting for Viking 1 to tell them whether it had survived landing on Mars. The signal would take 19 minutes to reach Earth, traveling at the speed of light across 212 million miles of space, which meant that whatever was happening on Mars right now, success, failure, silence, had already happened 19 minutes ago. They were watching the past arrive, and when the first images finally flickered onto screens, showing rocks and sand and a salmon-colored sky, humanity touched Mars for the first time. Not with hands, but with cameras and sensors, with the patient mechanical eyes of robots sent to see what we could not yet see ourselves. But reaching that moment required decades of failure, learning, trying again. The first attempts to touch Mars were disasters that taught us just how difficult it is to cross interplanetary distances and land softly on a world we'd only ever seen from far away. The Soviet Union tried first. In 1960, two probes, Marsnik 1 and Marsnik 2, were launched toward Mars but failed to leave Earth orbit. The rockets malfunctioned. The spacecraft fell back into atmosphere and burned up before they could begin their journey. In 1962, three more attempts. Mars 1 launched successfully, began its trajectory toward Mars, then went silent 3 months into the flight when its antenna system failed. The probe drifted past Mars in June 1963, dead and unreachable, humanity's first piece of interplanetary debris. The other two 1962 attempts never made it out of Earth's gravity well. 5 attempts. 5 failures. Mars was proving harder to reach than anyone had anticipated. The distance wasn't just physical, It was a distance of knowledge, of understanding what it took to build machines that could survive months in space, navigate across millions of miles, and arrive at a precise location at a precise time. The Americans tried in 1964. Mariner 3 launched in November, but its protective shroud failed to separate, leaving the spacecraft trapped, unable to deploy solar panels or navigate properly. It became another piece of silent metal drifting through the solar system. Mariner 4 launched 3 weeks later with an improved shroud design. This time, everything worked. The spacecraft traveled for 7.5 months, making tiny course corrections, with its attitude control thrusters using the stars to navigate following a trajectory calculated by human mathematicians using slide rules and early computers. On July 14, 1965, Mariner 4 flew within 6,118 miles of Mars's surface, the first successful Mars flyby in human history. It took 22 pictures as it passed, using a tape recorder to store the images, then slowly transmitted them back to Earth over the following weeks. Each image took 8 hours to transmit. The resolution was low, about 200 times worse than a smartphone camera today. But they showed something no human had ever seen: the surface of Mars up close in detail. And it was devastating. The images showed craters, just craters, ancient weathered impact, scars covering the surface like smallpox, suggesting a dead world with no atmosphere to protect it, no geological activity to erase the scars of bombardment, no water to smooth the landscape. Mars looked like the moon, cold, airless, utterly lifeless. The pressure readings confirmed it. Mars's atmosphere was about 1% as thick as Earth's, far too thin to support liquid water or protect against radiation. The dream of Martian civilization died that day. The canal myth finally collapsed under the weight of actual evidence. Mars wasn't inhabited. Mars wasn't dying. Mars was already dead and had been for a very long time. The scientific community reeled. Public interest in Mars plummeted. Why study a dead rock when there were more interesting targets? Venus's clouds, Jupiter's moons, Saturn's rings. Mars became briefly an astronomical footnote, a disappointing world that hadn't lived up to our expectations. But a few scientists looked at those crater images and asked different questions. How old were those craters? What was the surface made of? Were there any signs of past geological activity, even if nothing was happening now? The Mariner missions continued. Mariner 6 and 7 in 1969, both successful flybys that returned more images, more data, more evidence of a cratered, apparently dead surface. But they also found something interesting: variations in surface composition. Some regions were darker, some lighter. Some areas showed layered terrain. The southern highlands were ancient and heavily cratered, but the northern plains were smoother, younger, less scarred. Mars had geological history, even if it didn't have geological present. Something had happened there once long ago. Mariner 9 arrived at Mars in November 1971, with a more ambitious mission not to fly past, but to enter orbit and stay mapping the entire planet over months instead of hours. It was the first spacecraft to orbit another planet, a technical achievement that required precise navigation and a perfectly timed engine burn to slow down enough for Mars's gravity to capture it. The burn worked. Mariner 9 settled into orbit, and immediately the scientists encountered a problem: they couldn't see the surface. Mars was experiencing a planet-wide dust storm, the largest ever observed, covering the entire globe in a haze of suspended particles. For weeks, the spacecraft took pictures of nothing but featureless orange clouds. Engineers worried the storm would never clear, that the mission would fail despite reaching Mars successfully. But they waited, and slowly over months, the dust settled. Features began to emerge from the haze. First 4 dark spots at regular intervals near the equator, the peaks of volcanoes so tall they stuck up through the dust storm. Then valleys, networks of channels, features that looked nothing like impact craters. Mars was revealing itself as more complex than anyone had imagined. The images Mariner 9 sent back over the following year changed everything. Olympus Mons, a volcano 3 times taller than Mount Everest, so massive it would cover the entire state of Arizona. Valles Marineris, a canyon system stretching 2,500 miles long and up to 7 miles deep, making the Grand Canyon look like a scratch. And most importantly, dried river valleys branching networks of channels that looked exactly like water-carved features on Earth. The canals Lowell had imagined didn't exist, but real water channels did not straighten out artificial, but organic and natural, shaped by flowing liquid billions of years ago. Mars had been wet once. Mars had climate. Mars had weather and erosion, and all the processes that make a world dynamic and alive. It just didn't anymore. The dead Mars we'd been studying was actually a fossil, the preserved remains of a world that had died slowly over geological time, leaving its bones visible for anyone patient enough to look closely. This realization changed the mission for the next generation of Mars exploration. The goal wasn't to find current life, but to understand past life, or at least past habitability. If Mars once had water, it once had the basic requirement for life, as we understand it. Whether life actually emerged was an open question, but the possibility existed. And that possibility was enough to justify landing there, touching the surface, directly analyzing soil and rock and atmosphere, with instruments sophisticated enough to detect organic molecules if they existed. The Viking program was designed to do exactly that: land safely, survive on the surface, and search for signs of life past or present. Building a Mars lander in the 1970s required solving problems nobody had ever faced. How do you design a heat shield that can survive entering Mars's thin atmosphere without burning up or bouncing off? How do you slow down from thousands of miles per hour to zero in the few minutes between hitting atmosphere and hitting ground? How do you ensure your parachutes deploy correctly in air, 1% as thick as Earth's? How do you design landing legs that can handle any angle, any terrain, any surface hardness without tipping over? And how do you do all of this autonomously with no possibility of human intervention? Because the signal delay makes remote control impossible. Every decision had to be baked into the spacecraft's programming before launch. If something went wrong during landing, the lander would have to solve it itself, or die trying. Viking 1 launched on August 20th, 1975. It took almost 11 months to reach Mars, entering orbit in June 1976. The lander separated from the orbiter on July 20th and began its descent. The heat shield hit Mars's atmosphere at 10,000 miles per hour, slowing through friction until parachutes could deploy safely. Then the parachutes opened, slowing further. Then retro rockets fired burning hydrazine to provide the final deceleration. And then silence. 19 minutes of it, while radio waves crawled back to Earth, carrying the news of what had already happened. When the signal finally arrived, confirming successful landing, the room erupted. Engineers cried, strangers hugged. Champagne appeared from desk drawers. For the first time in 4 billion years, something from Earth was sitting on Mars, functional and alive. The first image took 4 minutes to transmit, arriving line by line, as the data slowly reconstructed itself into a picture. It showed Viking 1's own footpad sitting in rust-colored dirt rocks, scattered nearby, a flat horizon in the distance. The second image showed a wider view, more rocks, more sand. A landscape that looked almost familiar, like a desert on Earth, but the wrong color. The sky was pink, not blue, because dust particles in the thin atmosphere scattered light differently than air molecules on Earth. The sun appeared smaller, about 2/3 the size it appears from Earth, because Mars is farther away. The temperature readings showed -90 degrees Fahrenheit and dropping as Martian evening approached. The wind was blowing at about 15 miles per hour, creating small drifts of dust against rocks. Mars wasn't silent. It had weather motion, a kind of life, even if not biological life. It was a place, not just a point of light. And we were there. Viking 2 landed on September 3, 1976, at a site 600 miles away from Viking 1, providing a second set of eyes, a second location to study. Both landers carried identical instruments, cameras to photograph the landscape, a weather station to measure temperature pressure, and wind seismometer to detect Mars quakes, a scoop on a robotic arm to collect soil samples, and most importantly, 3 biological experiments designed to detect life by looking for chemical signs of metabolism. The experiments were clever. They would add nutrients to Martian soil and watch for gases that living organisms might produce, or they'd expose soil to light and carbon dioxide to see if anything photosynthesized, or they'd add radioactive carbon to soil and detect if organisms incorporated it into their cells. If Mars had bacteria, even dormant ones, these experiments should wake them up and make them visible through their chemistry. The results were confusing. Some tests gave positive results that looked like biological activity. Others gave negative results or weird results that didn't match what biology should produce. Scientists argued for months about interpretation. Eventually, the consensus formed. The positive results were probably chemical, not biological. Mars's soil contained oxidizing compounds, peroxides and superoxides created by ultraviolet light hitting the surface in the absence of a protective ozone layer. These compounds reacted with the organic nutrients in ways that mimicked biology, but weren't actually alive. Mars's soil was chemically aggressive, actively hostile to organic molecules. If life existed there now, it would have to be deep underground, protected from surface chemistry and radiation. The surface itself appeared sterile, scoured clean by chemistry and light over millions of years. The Viking experiments didn't find life, but they found something almost as interesting: a world so chemically active that it destroyed organic molecules on contact. Mars wasn't passively dead. It was actively killing anything organic that landed on it. Both Viking landers operated far longer than their designed lifetimes. Viking 1 continued sending data until November 1982, 6 years after landing. Viking 2 lasted until April 1980. They photographed dust devils swirling across the plains. They watched frost form and sublimate with seasonal changes. They measured atmospheric pressure rising and falling as carbon dioxide froze at the poles in winter and evaporated in summer. They showed us a dynamic world, cold and harsh, but not static, where weather happened, where the surface changed, where geological time was still ticking, even if nothing lived there anymore. The Vikings didn't find life, but they found a world worth understanding for its own sake, independent of whether it hosted biology. After Viking Mars exploration went quiet for 20 years, budgets tightened, public interest waned. Several Russian and American missions failed or were canceled. The Mars Observer probe was lost in 1993 just before entering orbit. The Mars 96 probe never left Earth orbit. Mars seemed cursed again, punishing our attempts to study it, defending its secrets through mechanical failure and bad luck. But the lessons from Viking guided the design of future missions. Engineers understood now what worked: airbags for landing smaller rovers instead of stationary landers, orbital mapping to find interesting sites before landing. The next generation of Mars exploration would be more mobile, more targeted, more capable of finding the specific places where past habitability was most likely. Mars Pathfinder landed in July 1997 using airbags to cushion its impact, then deploying a small rover called Sojourner, the first wheeled vehicle on another planet. Sojourner was tiny, about the size of a microwave oven, moving at 1 centimeter per second. But it could drive to different rocks, analyze their composition. With an X-ray spectrometer, photograph the landscape from multiple angles. It was the first hint of what true exploration might look like. Not one viewpoint from a stationary lander, but mobile investigation. The ability to see over hills, drive to interesting features, cover ground the way a human explorer would. Sojourner operated for 83 days, far longer than its designed 7-day mission, traveling about 100 meters and analyzing 16 rocks. It showed that mobile exploration was possible, that rovers could navigate Martian terrain, that the engineering challenges of building a vehicle for another planet were solvable. The next rovers were larger. Spirit and Opportunity landed in January 2004, each one the size of a golf cart, carrying sophisticated instruments, cameras that could see in color and zoom in on details, spectrometers that could identify minerals, a rock abrasion tool that could grind into stones to see fresh, unweathered surfaces. Both rovers were designed to last 90 days. Spirit operated for 6 years. Opportunity lasted 14 years, finally going silent in 2018 after a planet-wide dust storm covered its solar panels. Together, they drove dozens of miles, climbed hills, photographed thousands of rocks, and found undeniable evidence that liquid water had once been abundant on Mars. Not just occasional floods, but persistent water lakes that existed for years or centuries, groundwater that soaked the soil and altered minerals, creating hydrated clays and sulfates that still exist in the rocks today. Mars had been wet long enough for complex chemistry to occur, maybe long enough for life to start if conditions were right. Curiosity landed in August 2012, even larger, the size of a small car powered by a plutonium generator, instead of solar panels, carrying a chemistry lab sophisticated enough to identify organic molecules. Perseverance joined it in February 2021 with instruments specifically designed to look for biosignatures, chemical or physical evidence that life once existed preserved in ancient rocks. Both rovers are still operating, slowly climbing through geological time, examining layers of rock that record Mars's history like pages in a book. They're reading backwards from present to past, trying to find the moment when Mars went from habitable to hostile, trying to understand what went wrong and whether life had time to emerge before the water disappeared. We've come so far from those first Viking images, from stationary landers photographing rocks within arm's reach, to mobile laboratories driving miles across ancient lake beds collecting samples, listening to winds, watching eclipses, experiencing Mars as a place. Each mission teaches us how to do the next one better. Each landing, whether successful or not, adds to our understanding of what works and what doesn't. We're learning Mars the way you learn a person, slowly through repeated contact, through paying attention to patterns, through asking better questions based on previous answers. The robots we send are our eyes and hands, our patience and curiosity, our stubborn insistence on understanding this red world that has fascinated us for thousands of years. They're touching Mars so that someday maybe we can touch it ourselves. And with each touch, with each sample analyzed, and each image transmitted back across millions of miles of darkness, Mars becomes less alien, more familiar, more real. Not the Mars of myth or fantasy, but the actual planet with its own history and personality, its own story of birth and transformation and slow decline. A story we're finally learning to read one robotic footprint at a time. The silence between worlds is shrinking. The distance remains vast, but our reach extends farther with each decade. Mars is no longer just something we see. It's somewhere we've been, and the data flowing back from those far-off machines is revealing secrets that have waited 4 billion years to be discovered, hidden in plain sight, waiting for someone to get close enough to notice what the rocks and soil have been trying to tell us all along. Water has memory. Not consciousness, not thought, but chemical memory. The way it carves valleys, deposits minerals, alters rock structures in patterns that persist long after the water itself has vanished. On Earth, we read these patterns constantly without thinking about it. Smooth river stones tell us water flowed here. Sedimentary layers reveal ancient lake beds. Salt deposits mark where seas evaporated. Mars has these same signatures written in geology, billions of years old, preserved in the dry cold, like messages in a bottle thrown across time. The water is gone, now turned to vapor, that solar winds stripped away molecule by molecule or frozen into subsurface ice that will never melt again. But the memory remains. And that memory tells a story of a world that was once blue and alive with motion, where waves crashed against shorelines, where rivers carved through mountains, where rain fell from clouds and collected in valleys, feeding lakes that lasted long enough to lay down hundreds of feet of sediment. Mars had an ocean, not metaphorically, not theoretically, but actually a body of water covering perhaps a third of the northern hemisphere, holding more water than the Mediterranean Sea. And we can prove it reading evidence that the water itself left behind when it disappeared into the thin air of a dying atmosphere. The first hints came from orbit. The Mars Global Surveyor, which arrived in 1997, carried a laser altimeter, an instrument that bounced light off the Martian surface and measured how long it took to return, building a precise topographical map of the entire planet. When scientists analyzed the elevation data, they noticed something remarkable. The northern lowlands are smooth and flat, sitting about 4 miles lower than the southern highlands, with a sharp boundary between them. The boundary isn't perfectly circular, but it follows a consistent elevation contour that runs for thousands of miles, interrupted only by later volcanic formations and impact craters. It looks in every meaningful way like a shoreline. The kind of boundary you'd find where water meets land, where waves lap against beaches, where the geology changes from submerged to exposed. And it's at exactly the elevation where an ocean would form if Mars had enough water and atmospheric pressure to maintain liquid at its surface. The northern lowlands would be ocean floor. The southern highlands would be continents. The boundary between them would be coast. Mars had geography, not just geology. It had a division between sea and land that shaped its climate, its weather patterns, its potential for life. But elevation alone isn't proof. Boundaries can form. For many reasons, asteroid impacts, volcanic flows, tectonic processes. The real evidence comes from mineralogy, from the specific types of rocks and clays that only form in the presence of liquid water, sometimes requiring years or decades of submersion to develop their characteristic structures. The Mars Reconnaissance Orbiter, which arrived in 2006, carries spectrometers that can identify minerals from orbit by analyzing the wavelengths of sunlight they reflect. It found phyllosilicates clay minerals that form when water slowly alters volcanic rock, breaking down minerals like pyroxene and olivine into hydrated clays. These clays are everywhere in Mars's oldest terrains, the highlands that date back over 3.8 billion years. But they're especially concentrated in valley networks and crater basins, places where water would have pooled and persisted. Phyllosilicates don't form in ice. They don't form from vapor. They require liquid water in contact with rock for extended periods, sometimes centuries, allowing chemical reactions to proceed slowly, molecule by molecule, transforming one mineral into another. The Opportunity rover found hematite at Meridiani Planum, an iron oxide that on Earth typically forms in the presence of water, either in hydrothermal systems or in shallow lakes where iron-rich water evaporates slowly. But more importantly, Opportunity found hematite in small spherical formations that the science team called blueberries, because of their round shape and dark color. These spherules formed when iron-rich groundwater percolated through sedimentary rock, depositing iron minerals in concentrated spots that grew larger over time, layer by layer, like pearls forming in oysters. On Earth, these structures only form in aquifers, in regions of persistent groundwater flow. Mars had groundwater. Water didn't just flow on the surface, it soaked into the ground-filled pores in rock-created saturated zones, where chemistry proceeded in the dark, transforming the subsurface over millions of years. Perhaps the most striking evidence comes from sulfates minerals that form when water rich in sulfuric acid evaporates. Opportunity spent years exploring sulfate-rich layered formations at Endurance Crater and Victoria. Crater examining rock outcrops that showed fine horizontal layers, sometimes cross-bedded where ancient currents had deposited sand at angles, creating patterns identical to desert sandstone on Earth, but formed underwater. These weren't river deposits, they were lake deposits. Opportunity was driving across the floor of an ancient lake that had filled and dried multiple times each cycle, leaving a new layer of sediment that compressed into rock over billions of years. The chemistry varied between layers, suggesting the water composition changed, sometimes fresh, sometimes salty, sometimes acidic. Mars's water wasn't static. It had cycles, chemistry variability. It had weather driving it, geology influencing it, atmosphere interacting with it. It was part of a system, not just puddles sitting on stone. The Curiosity rover found even more detailed evidence at Gale Crater, which it's been exploring since 2012. Gale Crater contains a mountain in its center, Mount Sharp, rising over 3 miles high, composed entirely of sedimentary layers. This is unusual. Impact craters don't normally have central mountains made of sediment. The structure suggests the entire crater once filled with sediment deposited by water and wind over millions of years, then eroded back down until only the central peak remained. Curiosity has been climbing this mountain for years, driving up through geological time, examining layers that get progressively younger with elevation. The lower layers contain mudstone compressed mud that formed in lake bottoms where fine particles settled out of still water. The structure of the mudstone shows ripple marks and polygonal cracks identical to mud cracks on Earth, formed when wet sediment dries and shrinks. Mars had wet seasons and dry seasons. It had climate variability that affected water availability. It wasn't a static environment, but a dynamic one where conditions changed, where lakes filled during wet periods and partially dried during droughts, exposing mud to air and sunlight. But here's what makes Gale Crater's lake especially interesting. It was persistent. The mudstone layers are thick hundreds of feet in some locations, representing millions of years of continuous deposition. This wasn't a brief flood or a temporary puddle. This was a stable lake that existed long enough to accumulate serious sediment, long enough for chemistry to occur, long enough that if life had been present, it would have had time to establish itself, adapt to conditions, potentially leave behind biosignatures we might still be able to detect. Curiosity is looking for exactly those signatures, drilling into rocks and analyzing the powder for organic molecules. It's found them simple organic compounds, carbon-based molecules that could come from life, but could also come from non-biological sources like meteorites or chemical reactions in the rock itself. The challenge is distinguishing between biological and geological organics, which requires looking for patterns, specific molecules in specific ratios that life tends to produce. That work is ongoing. The molecules are there. The interpretation is still developing. The Mars Reconnaissance Orbiter discovered something else in 2015 that changed our understanding of Martian water evidence, that liquid water still exists occasionally on the surface today. High-resolution images showed dark streaks appearing on steep slopes during warm seasons, then fading during cold seasons. The streaks, called recurring slope lineae, start at the top of slopes and flow downward, lengthening over time before disappearing. Spectroscopic analysis showed they contain hydrated salts, perchlorates, and chlorates that lower water's freezing point, allowing brine to remain liquid at temperatures where pure water would freeze. The hypothesis is that these streaks are caused by very salty water, seeping from subsurface aquifers, flowing briefly on the surface before evaporating or soaking back into the ground. They're seasonal, temporary, and tiny, just a few meters wide and a few hundred meters long. But they represent active water on Mars right now, not just ancient water from billions of years ago. Mars isn't entirely dead. It's dormant, with occasional liquid water events happening even in the current, cold, thin atmosphere conditions. Delta deposits provide another compelling water signature. River deltas form where flowing water enters a standing body of water, slows down, and drops its sediment load, creating a fan-shaped deposit with characteristic layering patterns. Mars has delta deposits. Jezero crater contains a particularly well-preserved one, which is why NASA chose it as the landing site for Perseverance rover. Orbital images show the classic fan shape with layers of sediment visible in cliff faces where erosion has cut through the deposit. The Perseverance rover is now exploring this delta, directly examining the layering up, close drilling samples that will eventually be returned to Earth by a future mission. If Mars ever hosted life, a lake delta is one of the best places to look. It's where organic material from the watershed would accumulate, where nutrients would concentrate, where different environments would overlap, creating ecological boundaries that on Earth are hotspots for biodiversity. But perhaps the most ambitious water research comes from subsurface radar, the Mars Advanced Radar for Subsurface and Ionosphere. Sounding MARSIS on the Mars Express orbiter can send radar pulses that penetrate several miles into Mars's crust, bouncing off layers of different density and returning signals that reveal subsurface structure. In 2018, Mars's data revealed a bright reflection beneath the South Polar ice cap, about a mile underground, extending over 12 miles in area. The reflection pattern matches liquid water, specifically a subsurface lake of extremely salty brine, kept liquid despite sub-freezing temperatures by high concentrations of dissolved salts. Additional analysis found more potential subsurface lakes in the same region. If confirmed, these would be the largest bodies of liquid water on Mars, today protected from evaporation and radiation by miles of ice and rock, persisting in the cold dark like underground reservoirs waiting to be explored. Could they harbor life? Possibly. Earth has microbes that live in similar environments. Subglacial lakes in Antarctica host bacterial communities that survive in permanent darkness, feeding on minerals dissolved in the water and chemical energy from rock interactions. If Mars has similar conditions, it might have similar life isolated from the surface for millions of years, evolving independently, representing a second origin of life in our solar system. Think about what all this evidence means when you put it together. The phyllosilicates tell us Mars had water for millions of years in its early history. The hematite spherules tell us that water percolated through the ground, creating aquifers. The sulfate layers tell us lakes filled and evaporated repeatedly. The deltas tell us rivers flowed from highlands to lowlands, carrying sediment and organic material. The shoreline boundaries tell us water collected in a northern ocean. The recurring slope lineae tell us tiny amounts of liquid water still flow seasonally. The subsurface lakes tell us large volumes of water still exist hidden underground. Mars wasn't briefly wet and then dry. Mars was wet for perhaps 1 billion years during its early history, with multiple water systems operating simultaneously. Surface oceans, groundwater, rivers, lakes, seasonal flows. It was a hydrological cycle comparable to Earth's, driven by its atmospheric circulation, maintained by greenhouse warming from a thicker atmosphere. What happened? Why did all that water disappear? The answer lies in Mars's small size. Mars is about half Earth's diameter and only 11% of Earth's mass. This small size meant its interior cooled faster than Earth's, and when the core cooled sufficiently, the planet's magnetic field generated by liquid iron convection in the core shut down. We know this happened because Mars's ancient crust contains magnetized minerals that froze in place about 4 billion years ago, when the field was still active, but younger rocks show no magnetization. The field turned off. And without a magnetic field, Mars lost its primary defense against solar wind, the stream of charged particles constantly flowing away from the sun. On Earth, our magnetic field deflects most solar wind, protecting our atmosphere from being stripped away. Mars had no such protection. Solar wind hit the upper atmosphere, directly giving atoms enough energy to escape Mars's relatively weak gravity. Oxygen molecules were split into atoms, Hydrogen was blown away, carbon dioxide slowly evaporated into space. The atmosphere thinned over hundreds of millions of years. As it thinned, pressure dropped. As pressure dropped, liquid water became unstable. It would either freeze or evaporate, unable to exist as liquid for more than brief moments. The ocean evaporated its water molecules, dissociating and escaping to space. The lakes dried, the rivers stopped flowing. The groundwater froze deep underground, or slowly diffused upward and evaporated. Within perhaps 500 million years of the magnetic field, failure Mars transformed from a potentially habitable world to a frozen desert. But 500 million years is a long time. On Earth, life emerged within the first billion years of the planet's history, possibly as early as 800 million years after formation. If life follows similar timelines elsewhere, then Mars had enough time for biology to start to establish itself to diversify. Whether it actually did is unknown, but the window was open. The conditions were right. Water, energy, organic chemistry, stable environments, all the ingredients we know life requires. If life started on Mars, what happened to it when the water disappeared? Some might have gone extinct. But some might have adapted, moving underground, where water still existed, evolving to survive in extreme conditions, persisting in tiny refuges where liquid water occasionally appears, waiting in a kind of suspended animation for conditions to improve. Or it might have gone completely extinct, leaving behind only chemical signatures and fossil remains buried in ancient lake beds and delta deposits, waiting for someone to find them and recognize what they are. This is why Mars fascinates us now, in ways it never did when we thought it was simply dead. It's not dead, it's dormant. It's not barren, it's transformed. It's not a rock, it's a tomb, containing the remains of a world that lived and died, and possibly a biosphere that lived and died with it. Every rock we analyze, every soil sample we study, every layer we examine could contain the answer to one of humanity's deepest questions: are we alone? Did life emerge only on Earth, or is it a natural consequence of chemistry that happens wherever conditions permit? Mars is our best chance to answer that question without leaving the solar system. It's close enough to reach. It was habitable long enough to give life a chance. It's preserved enough evidence that we can reconstruct its history. And it's still active enough that perhaps in protected pockets, life persists even now, waiting to be discovered. The water remembers. It left its signature in clay minerals and sulfate deposits in valley networks, and delta formations and shoreline boundaries and subsurface lakes. It tells us Mars was worth living on once. Whether anything actually lived there is the question driving every Mars mission launched in the past decade. We're not just studying geology anymore. We're doing archaeology on a planetary scale, excavating the past of an entire world, trying to determine whether it ever hosted the phenomenon we call life. The evidence mounts with every discovery. The story becomes clearer with each rover track across ancient lake beds. Mars had water. Mars had time. Mars had all the ingredients. Whether it had life, that's what we're here to find out. And the answer, whatever it is, will change how we see ourselves, how we understand our place in the cosmos, how we think about the probability of consciousness emerging from chemistry. Because if life started independently on both Earth and Mars, two planets in the same solar system, then life is probably common throughout the universe, waiting to be found anywhere conditions permit. But if Mars was habitable and remained lifeless, if chemistry alone wasn't enough, then maybe Earth is special. Maybe we're rare. Maybe the universe is mostly silence and rock, with only rare islands of biology struggling against entropy. Mars holds the answer. The water wrote it down billions of years ago. We just need to learn how to read what it preserved in the stone. Silence on the surface doesn't mean silence below. On November 26, 2018, a spacecraft called InSight touched down on Elysium Planitia, a flat expanse of Martian plain chosen specifically for its boring geography. No hills, no rocks, just endless dust, stretching to the horizon. The mission wasn't there to explore or drive around. It was there to listen, to place a seismometer on the ground, cover it with a protective dome, and wait for Mars to speak through vibrations traveling through stone. For months, nothing. Just wind noise thermal creaks the spacecraft's own mechanical sounds. Then on April 6, 2019, the instruments detected something different. A faint tremor magnitude 2.5 lasting several minutes, originating somewhere deep inside the planet. Mars had a heartbeat. Faint, irregular, but real. The planet we'd call dead was moving inside, processing, transforming, living a slow internal life invisible from the surface. And that discovery changed everything we thought we knew about how dead worlds behave. InSight's mission was to answer questions that rovers can't address. Surface exploration tells us about Mars's past, the water that flowed the atmosphere that vanished the geology that eroded. But understanding Mars's present requires looking inward at the structure hidden beneath kilometers of rock, at processes happening too slowly to see, but fast enough to matter over geological time. Is Mars's core still molten? Does it have tectonic activity? How thick is the crust? What's generating the heat that keeps the interior warm when the surface is frozen? These questions require seismology, the same technique we use on Earth to map subsurface structure by analyzing how seismic waves travel through different materials. InSight carried the most sensitive seismometer ever sent to another planet, capable of detecting ground movement smaller than the width of a hydrogen atom. It could hear a Marsquake on the opposite side of the planet, feel vibrations from dust devils passing hundreds of meters away, sense thermal expansion as rocks warmed and cooled with day and night. It was designed to listen to everything Mars had to say. The first Marsquakes were disappointing, honestly. Small, distant, barely detectable above background noise. Nothing like the magnitude 7 or 8 earthquakes that shake our planet regularly. Mars seems seismically quiet, its interior settled and inactive. But InSight kept listening, and the Marsquakes kept coming. Over 4 years of operation, the seismometer detected over 1,300 seismic events ranging from magnitude 2 to magnitude 5. The distribution wasn't random. Certain regions produced more quakes than others, suggesting localized stress zones, where the crust is still adjusting, still settling into equilibrium after billions of years of cooling. The largest event, a magnitude 4.7 quake in May 2022, sent shockwaves through the planet, powerful enough to reveal internal structure with unprecedented clarity. Scientists analyzed how long the waves took to travel through different layers, how their speed changed as they passed through materials of different density, how they reflected off boundaries between regions. The data painted a picture of Mars's interior more detailed than anyone had expected to achieve with a single lander. Mars has a core about 830 kilometers, in radius larger than expected, which means it's less dense than we thought, probably containing lighter elements like sulfur mixed with iron and nickel, and crucially, it's liquid. Not solid like Earth's inner core, but molten, still convecting, even though Mars is smaller and should have cooled faster. This matters because liquid cores can theoretically generate magnetic fields if the convection is fast enough and the planet rotates sufficiently. Mars doesn't have a global magnetic field now, but the liquid core means it's not impossible if conditions changed. If the convection patterns shifted, the field might restart. It's sleeping, not dead. The mantle above the core is thick, about 1,500 kilometers, cooler than Earth's mantle, but not completely solid. Seismic data suggests parts of it still have partial melt pockets of magma that haven't fully crystallized zones, where heat from radioactive decay keeps rock at temperatures where it can flow like thick honey over millions of years. This slow convection drives what little geological activity Mars still has, pushing up volcanic regions like Tharsis and Elysium, fracturing the crust in places generating the Marsquakes InSight detected. The crust is surprisingly thin in places as little as 20 kilometers in some regions compared to Earth's average of 40 kilometers. A thin crust means Mars's interior is closer to the surface than we expected, which has implications for heat flow, for volcanic potential, for the possibility of accessing subsurface resources or detecting subsurface life. It also explains why Mars has such dramatic volcanic features. Olympus Mons and the other Tharsis volcanoes formed because lava could reach the surface more easily, through thinner crust, building up over millions of years into mountains that dwarf anything on Earth. These volcanoes aren't active now, but they're not extinct either. Extinct means they'll never erupt again. Mars's volcanoes are dormant, inactive now, but capable of reactivating if magma pressure builds sufficiently. Some volcanic regions show lava flows that are geologically young, only a few million years old, suggesting Mars had volcanic activity within the time frame of human evolution on Earth. It's not ancient history, it's recent history on geological scales. InSight also detected something: unexpected magnetic anomalies. Mars doesn't have a global magnetic field anymore, but it has local magnetic fields frozen into ancient crustal rocks, remnants of the time when Mars did have an active dynamo 4 billion years ago. These crustal magnetic fields are 10 times stronger than scientists predicted, suggesting Mars's ancient field was comparable in strength to Earth's current field. The rocks at InSight's landing site are magnetized so strongly that they affect the lander's own instruments, creating interference that had to be carefully calibrated out of measurements. This strong magnetization tells us Mars wasn't just weakly magnetic in its youth. It had a vigorous protective magnetic field that should have been capable of shielding the atmosphere from solar wind, at least for a while. The fact that the atmosphere was still lost despite this protection suggests the loss happened gradually after the field shut down over hundreds of millions of years, not catastrophically. Mars had time. If life existed, it would have had centuries to adapt as conditions slowly deteriorated. But perhaps the most tantalizing discovery came from radar data, not seismic data. The Mars Advanced Radar for Subsurface and Ionosphere, sounding on Mars Express, which we mentioned briefly before, sent radar pulses deep into Mars's crust and detected bright reflections beneath the south polar ice cap. Reflections consistent with liquid water. In 2018, researchers announced they'd found a subsurface lake about 20 kilometers wide, buried under 1.5 kilometers of ice. The lake exists because it's not pure water. It's brine, heavily salted with perchlorates that lower the freezing point to minus 68 degrees Celsius. At that temperature, even the sparse geothermal heat seeping up from Mars's interior is enough to keep the brine liquid. Follow-up observations found more lakes nearby, suggesting an entire system of subglacial water bodies interconnected or isolated, existing in the cold darkness beneath the polar ice. Why does this matter so much? Because liquid water is the universal solvent, the medium where chemistry happens efficiently, the requirement for life as we understand it. If Mars has persistent liquid water underground, protected from radiation and atmospheric loss, then it has environments where microbial life could theoretically survive indefinitely. Earth has analogs. Lake Vostok in Antarctica sits under 4 kilometers of ice, isolated from the surface for millions of years. Yet when scientists finally sampled it, they found bacterial communities thriving in the cold darkness, feeding on minerals dissolved from the bedrock, surviving without sunlight or organic input from the surface. If Lake Vostok can support life, Martian subglacial lakes might support life too. Different life adapted to different chemistry, but life nonetheless. There's precedent for this. Earth's deep biosphere microbial communities living in rock pores and fractures kilometers below the surface comprises an enormous biomass, possibly comparable to all surface life combined. These organisms don't photosynthesize. They don't need oxygen. They extract energy from chemical reactions between rock and water, splitting hydrogen from minerals, using that energy to power metabolism. Some of these microbes have been isolated from the surface for millions of years, evolving in complete darkness, processing rock at rates so slow they divide perhaps once per century. They're alive, but barely existing at the absolute minimum energy threshold life requires. Mars could have similar organisms living in fracture zones, where groundwater persists in caves, where geothermal heat creates habitable pockets in the regolith itself, where tiny amounts of brine form during temperature fluctuations. They wouldn't be obvious. They wouldn't form visible colonies or produce detectable gases. They'd be invisible, microscopic, surviving in the margins, but alive. The InSight data also revealed something about Mars's day that nobody expected. By precisely tracking the lander's position using radio signals, scientists measured how Mars wobbles as it rotates, a wobble caused by the planet's non-uniform mass distribution and its liquid core sloshing around inside. The measurements showed Mars's rotation is accelerating, slightly speeding up by about 4 milliseconds per year. This might not sound like much, but it's measurable and it's real. Why is Mars spinning faster? Probably because of ice redistribution, carbon dioxide freezing at the poles in winter, then sublimating in summer, moving mass toward and away from the rotation axis, affecting angular momentum, the way a spinning ice skater speeds up when pulling in their arms. Mars has seasons, weather mass transport, active processes that affect the planet's rotation. It's dynamic in ways we're only beginning to measure. Another surprise, Mars rings like a bell. When meteorites hit the surface, they generate seismic waves that travel around the planet multiple times, bouncing between the surface and core boundary, slowly decaying over hours. By analyzing these reverberations, scientists can determine how energy disperses through Martian rock, which reveals material properties, density, elasticity, temperature. The data suggests Mars's mantle is more viscous than Earth's, meaning it flows more slowly, which explains why Mars doesn't have plate tectonics. The rock is too stiff to subduct and recycle the way Earth's plates do. Mars's crust is one solid shell, broken only by impact craters and volcanic vents, with no mechanism to pull old surface back into the interior. This means Mars's surface is a record. Everything that happened there stays visible, preserved, not erased by tectonic recycling. It's a geological archive, frozen in time, waiting to be read. InSight also monitored atmospheric pressure, continuously detecting tiny fluctuations caused by wind patterns, dust devils, seasonal changes. One finding stands out. Mars's atmosphere has a very regular rhythm, a pressure wave that circles the planet twice per day, driven by solar heating. As the sun moves across the sky, it heats the atmosphere, causing expansion and contraction that propagates as a pressure wave moving westward at about 1,000 kilometers per hour. This thermal tide is much stronger on Mars than on Earth, because Mars's thin atmosphere responds more dramatically to temperature changes. The wave affects dust-lifting cloud formation, weather patterns. It's a fundamental characteristic of Martian meteorology, and we only discovered it by sitting in one place and measuring pressure with extreme precision for years. Sometimes the most important discoveries come from patience, not exploration. What does all this underground activity mean for Mars's future? If the core is still liquid, if the mantle still has partial melt, if volcanic regions might still erupt, then Mars isn't finished evolving. It's in a slow phase, dormant rather than dead, but capable of reactivation if conditions change. What would it take to wake Mars up? More heat, probably. If we could somehow increase the temperature of the core, impossible with current technology, but theoretically conceivable, convection might speed up, potentially regenerating a weak magnetic field. Or if we could thicken the atmosphere significantly, greenhouse warming might raise surface temperatures enough to melt some subsurface ice, creating temporary liquid water on the surface. These aren't natural processes that will happen on their own. Mars's trajectory is toward increasing coldness and silence. but they might be possible with deliberate intervention, with planetary engineering on scales we can barely imagine. Mars might be terraformable, not in decades or centuries, but over thousands of years of patient work, building an atmosphere molecule by molecule, warming the surface degree by degree, coaxing water back to the surface where it hasn't flowed in billions of years. But even without terraforming, even in its current state, Mars's subsurface is potentially habitable. The water is there protected underground. The heat is there seeping up from radioactive decay and residual core warmth. The chemistry is there, rocks interacting with water to produce hydrogen and other energy sources. The time is there, billions of years of stable conditions, allowing any life that started to adapt and persist. We haven't looked yet, not really. Our rovers have only scratched the surface, literally drilling a few centimeters into rock, sampling the topmost layer of regolith. To find subsurface life, we'd need to drill meters or kilometers deep, accessing environments where radiation doesn't penetrate, where temperature stays above freezing, where water persists. That's technically difficult and expensive, but not impossible. Future missions might carry drills capable of reaching those depths, extracting samples from aquifers and fracture zones, analyzing them for chemical signatures of metabolism. If life exists on Mars, that's where it is hidden underground, waiting for someone to dig deep enough to find it. Have you ever wondered what Martian microbes would look like if they exist? Would they resemble Earth bacteria with similar biochemistry and cellular structure? Or would they be fundamentally alien, using different molecules, different energy sources, different solutions to the problem of staying alive? The answer would tell us whether life is convergent, whether chemistry always produces similar results given similar conditions, or divergent, capable of finding radically different paths to the same functional goal. Either answer would be profound. Convergence would suggest life is predictable, that the laws of chemistry constrain biology into certain forms, regardless of where it emerges. Divergence would suggest the opposite, that life is creative, exploratory, capable of solutions we haven't imagined, because we've only studied one example. Mars could answer this question. It's close enough to Earth that panspermia life spreading between planets via meteorite impacts is possible, which would make Martian life a cousin of Earth life sharing a common ancestor. Or it might represent an independent origin, a second genesis, proving that life isn't a fluke, but a natural outcome of chemistry, given the right ingredients. We won't know until we look, until we go underground, until we drill into the places where Mars's pulse is strongest and see what responds to our presence. The subsurface isn't silent. It's not empty. It's not finished with its story. Mars quakes ripple through stone, liquid water, hides in dark pockets. Volcanic chambers hold magma that might someday erupt. Microbes might metabolize in the slow darkness, processing minerals and water at speeds so gradual they're almost geological. Mars's interior is a world we haven't explored yet, accessible only through indirect measurement and inference, waiting for the technology that will let us reach it directly. And when we do, when we finally drill through kilometers of ice and rock and tap into those hidden lakes, when we lower cameras and sensors into Martian caves and fracture zones, we might find that the silence we've been interpreting as death is actually just restraint, that Mars has been alive all along, in the places we couldn't see, continuing its internal life while the surface slept, patient and persistent, waiting for someone to notice that beneath the dust and cold, a heartbeat continues faint but steady, the pulse of a world that refused to die completely, even when everything on its surface did. Gas molecules don't lie, but they don't always tell the truth either. In June 2013, the Curiosity rover detected something in Mars's atmosphere that shouldn't have been there. Methane, a simple molecule of one carbon atom, bonded to 4 hydrogen atoms, appearing in concentrations that spiked and vanished with no clear pattern. On Earth, about 90% of atmospheric methane comes from living organisms, bacteria in wetlands, digestive processes in animals, decomposition of organic matter. The remaining 10% comes from geological sources like volcanic vents and hydrothermal systems. On Mars, neither source should exist. No active volcanoes, no visible life, no obvious mechanism to produce methane. Yet there it was measured repeatedly, varying seasonally, appearing in some locations, but not others, rising to detectable levels, then disappearing below instrument sensitivity within weeks. Scientists have been arguing about this methane for over a decade, proposing theories and counter-theories, conducting follow-up measurements, building models that explain parts of the data, but never all of it. The methane mystery remains unsolved, and that ambiguity, that gap between observation and explanation, is where the most interesting possibilities live. The story begins earlier than 2013, actually. In 2003, 3 independent teams using Earth-based telescopes announced they detected methane in Mars's atmosphere using spectroscopy analyzing sunlight reflected from Mars and looking for absorption lines characteristic of specific molecules. Methane has a distinct spectral signature at wavelengths around 3.3 micrometers, and all 3 teams saw it faintly but consistently. The concentrations were low, about 10 parts per billion, but measurable. The announcement generated excitement and skepticism in roughly equal measures. Excitement, because methane on Mars could indicate active biology, or at least active geology, both of which would mean Mars was more dynamic than we'd assumed. Skepticism, because detecting trace gases in another planet's atmosphere from Earth is technically difficult, prone to false positives from Earth's own atmospheric methane contaminating the signal. The observations needed confirmation from instruments actually on Mars measuring the atmosphere directly without interference from our own. That confirmation seemed to come in 2004 when the European Space Agency's Mars Express orbiter detected methane using its Planetary Fourier spectrometer. The instrument found methane concentrated in specific regions: Tharsis, Arabia, Terra, Neely, Phocea, suggesting localized sources rather than a uniform global distribution. If methane were simply left over from Mars's formation billions of years ago, it should be evenly mixed throughout the atmosphere by wind and diffusion. But it wasn't. It clumped in areas, implying active release, something producing methane recently enough that atmospheric circulation hadn't homogenized it yet. The Mars Express data suggested plumes of methane appearing and disappearing over months, sometimes correlating with seasons, sometimes not. The pattern was maddeningly inconsistent, which made it difficult to build a coherent explanation. But the detections were real. Multiple instruments, multiple observation periods, all finding the same molecule in similar concentrations. Then came the contradictions. In 2006, NASA launched the Mars Reconnaissance Orbiter, carrying an instrument called CRISM Compact Reconnaissance Imaging Spectrometer for Mars, capable of detecting methane from orbit with high sensitivity. CRISM looked for methane. It found nothing. Not low concentrations, not ambiguous signals, but complete absence with upper limits, suggesting less than 1 part per billion. How could Mars Express see methane plumes and CRISM see nothing? Were the detections false? Was the methane extremely localized, visible only under specific observing conditions? Was it seasonal, present only during times when one instrument looked, but not the other? The scientific community split into camps: believers who thought the methane was real and needed explanation, and skeptics who thought the detections were instrumental artifacts or data analysis errors. The debate became heated, personal at times, with careers and reputations entangled in competing interpretations of ambiguous data. Curiosity's arrival in 2012 promised to settle the debate. The rover carried the sample analysis at Mars Instrument, SAM, specifically designed to measure atmospheric composition by sucking in air, concentrating it, and analyzing it with gas chromatography and mass spectrometry. SAM could detect methane at concentrations below 1 part per billion, far more sensitive than any previous Mars instrument. For 8 months after landing, Curiosity ran atmospheric samples through SAM looking for methane. Nothing. Sample after sample showed concentrations below the detection threshold. The skeptics claimed vindication. The methane detections were false positives, and Mars's atmosphere was exactly as dead as a cold, geologically inactive planet should be. But then, in late 2013 and early 2014, something changed. Over a 2-month period, methane concentration spiked to 7 parts per billion, 7 times higher than before, then declined back to baseline levels. The spike wasn't a measurement error. It happened consistently across multiple samples taken over weeks. Mars had released a pulse of methane detected at ground level by an instrument sitting right there in the atmosphere, and then the methane had disappeared, destroyed, or dispersed by some mechanism that cleared it from the local atmosphere faster than anyone expected. Curiosity continued monitoring, and a pattern emerged. Background methane levels averaged about 0.5 parts per billion, barely detectable but consistently present. But superimposed on this background were occasional spikes, brief increases to several parts per billion lasting days or weeks, then vanishing. The spikes appeared seasonal, more common during late northern summer, suggesting a connection to temperature or atmospheric circulation. But they were also unpredictable. Some years showed spikes, other years didn't. Some locations showed methane, others didn't. The data was frustratingly inconsistent, refusing to resolve into a simple explanation. And the disappearance was especially puzzling. Methane on Mars should persist for about 300 years before being destroyed by ultraviolet light in the upper atmosphere, breaking down into carbon dioxide and water vapor. If methane is being released seasonally, it should accumulate, building up year after year until it reaches equilibrium between production and destruction. But that's not what Curiosity observed. The methane appeared and vanished on timescales of weeks, implying some mechanism was removing it much faster than photochemistry alone could explain. What could destroy methane that quickly on Earth, certain bacteria consume methane as an energy source, oxidizing it to carbon dioxide? Methanotrophs, they're called, and they're found in soils and wetlands where methane concentrations are high. Could Mars have methanotrophs? It's theoretically possible, but seems unlikely. Why would methane-consuming bacteria evolve if there's barely any methane to consume? The chicken and egg problem is difficult to resolve. More likely, the rapid methane destruction is chemical, not biological. Mars's surface contains perchlorates, highly oxidizing salts that react aggressively with organic molecules. Perchlorates in dust might oxidize methane at the surface, removing it from the atmosphere before it can accumulate. Or the methane might adsorb onto dust particles sticking to the surface and being carried away by wind, effectively removing it from the gas phase. These explanations are plausible, but unproven. Nobody has demonstrated in laboratory conditions that Martian dust destroys methane quickly enough to explain the observations. The mechanism remains speculative. Meanwhile, the source question remained unsolved. Where is the methane coming from? There are essentially 3 possibilities: geological, biological, or extraplanetary. The geological explanation suggests methane is produced by serpentinization, a chemical reaction, where water interacts with olivine-rich rock, producing hydrogen and methane in the process. This happens on Earth at hydrothermal vents and in subduction zones, and it doesn't require life. If Mars has subsurface water, which we know it does, and olivine-rich rock, which we also know it does, then serpentinization could produce methane slowly over time, releasing it through fractures and vents where it reaches the surface. The seasonal pattern might reflect groundwater availability or temperature variations that affect reaction rates. This is a clean, non-biological explanation that accounts for the observations without requiring life. Many scientists favor it because it doesn't invoke extraordinary claims. But there are problems with the geological explanation. Serpentinization produces hydrogen along with methane, and Curiosity has looked for hydrogen. It's not there, at least not in the concentrations expected if serpentinization were the source. Additionally, geological methane release should correlate with tectonic or volcanic activity. Mars has neither currently, and the regions where Curiosity detected methane don't align with ancient volcanic features or known fracture systems. The geology doesn't quite fit, leaving room for alternative explanations. The biological explanation is more controversial. If Mars has subsurface microbes, and if those microbes are methanogens, organisms that produce methane as a metabolic byproduct, then the seasonal methane releases could reflect biological activity responding to environmental changes. On Earth, methanogens are archaea primitive single-celled organisms that live in anaerobic environments like wetlands, deep soil, and animal guts. They produce methane by reducing carbon dioxide with hydrogen, a metabolic pathway that requires no oxygen and produces energy sufficient to sustain slow growth. If Martian subsurface environments contain similar organisms adapted to local chemistry and temperature, they might produce methane that seeps to the surface through soil pores and fractures, creating the plumes Curiosity detected. The seasonal variation could reflect temperature changes affecting metabolic rates, or water availability affecting population size, or atmospheric pressure variations affecting gas transport through soil. This explanation is exciting because it implies Mars hosts active biology, not fossil remnants, but living organisms processing resources right now. But it's also unfalsifiable with current data. We can't distinguish between geological and biological methane using concentration measurements alone. The molecule is identical regardless of origin. What we'd need is isotopic analysis measuring the ratio of carbon-12 to carbon-13 in the methane. Biological processes preferentially use lighter isotopes, so biological methane typically has a higher carbon-12 ratio than geological methane. SAM can measure isotopes in theory, but the methane concentrations Curiosity detected are so low that collecting enough for accurate isotopic analysis requires months of sampling. And by the time you've collected enough, the methane pulse has ended, and you're analyzing mixed samples from different sources and times. The isotopic data exists, but is ambiguous, inconclusive, consistent with either biological or geological sources, depending on how you interpret measurement uncertainties. The third possibility, extraplanetary origin, suggests the methane comes from space delivered by micrometeorites and comets that constantly bombard Mars's surface. Organic material in these objects breaks down under ultraviolet radiation, releasing methane along with other gases. This happens on all airless bodies and should happen on Mars too. The problem is, scale calculations suggest meteoritic infall should produce methane at rates far too low to explain the concentrations Curiosity detected. You'd need a massive increase in meteor impacts to account for the observations, and there's no evidence of such an increase. Extraplanetary sources probably contribute background methane, but they can't explain the spikes. So, we're left with a mystery that refuses resolution. Methane appears on Mars seasonally in concentrations that vary unpredictably from sources we can't identify, removed by mechanisms we don't understand, leaving behind questions that multiple missions and decades of observations haven't answered. This is actually typical of how planetary science works. We often detect phenomena before we can explain them. Observations precede understanding, sometimes by years or decades. The methane mystery isn't a failure of science, it's science in progress. The uncomfortable phase where data conflicts with expectations and competing theories all have flaws. Eventually, more measurements will narrow the possibilities. Future missions might carry more sensitive instruments, or drill deeper to sample subsurface gases directly, or place seismometers near suspected vents to listen for gas release events. Each new piece of data constrains the explanations, eliminating hypotheses that don't fit, strengthening those that do. But here's what keeps scientists awake at night: The possibility that the methane is biological, that we're detecting the metabolic exhaust of Martian organisms living in subsurface aquifers, and we're just not equipped yet to prove it. If that's true, then Mars isn't a dead world with interesting geology. It's a living world with an active biosphere hidden underground, where we can't easily access it, making its presence known through subtle chemical signals that require patience and precision to detect. That possibility, however remote, drives ongoing Mars exploration more than any other question. Because finding life beyond Earth wouldn't just answer whether we're alone, it would answer whether life is common, whether biology emerges naturally from chemistry anywhere, conditions permit, whether the universe is full of living worlds or mostly barren, except for rare exceptions like Earth. The methane mystery also highlights a broader challenge in astrobiology: ambiguity tolerance. Scientists are trained to demand certainty, to suspend judgment until evidence is conclusive. But planetary exploration operates at the edge of instrumental capability, where signals are weak and backgrounds are noisy, where you're measuring trace chemicals in an alien environment using instruments designed based on assumptions that might be wrong. You can't always achieve certainty. Sometimes you have to act on probability, on incomplete information, on hints and suggestions, rather than proof. The methane detections are real, multiple independent instruments have confirmed them, but what they mean remains open to interpretation. Do you invest billions of dollars in follow-up missions based on ambiguous data? Do you design life detection instruments for Mars when you can't be sure life is actually there? These are decisions made under uncertainty, betting on possibilities rather than certainties, accepting risk, because the potential reward, confirming life beyond Earth, is worth the gamble. There's also a methodological lesson here about the difference between detection and understanding. We can detect methane. That's the easy part. Build a sensitive spectrometer, point it at Mars, measure absorption lines. But detecting something doesn't mean understanding it. Understanding requires context, mechanism, reproducibility. It requires knowing not just that methane exists, but where it comes from, how it's produced, why it varies, how it's removed. Understanding requires years of follow-up observations, laboratory experiments that replicate Martian conditions, theoretical models that connect observations to physical processes. The gap between detection and understanding can take decades to bridge, and sometimes, as with Mars, methane, the bridge remains incomplete despite immense effort. What would it take to solve the methane mystery definitively? Probably direct sampling of the source. If the methane is geological, we need to find the vents releasing it, drill into them, sample the gases coming out, analyze their composition and isotopes. If it's biological, we need to access the subsurface environments where the organisms live. Extract samples, look for cells or biochemical markers. Both approaches require technology we don't currently have on Mars: deep drilling, rigs, subsurface access vehicles, sophisticated sample handling systems. Future missions might bring these capabilities. The Mars Sample Return Campaign, planned for the late 2020s and 2030s, will bring Martian soil and rock back to Earth, where we can analyze them with laboratory instruments far more powerful than anything we can send to Mars. If those samples contain methane-producing microbes or geological structures that generate methane, we'll know. Until then, we watch and measure and argue and wonder, trying to read meaning in gas concentrations that rise and fall with seasons whispering stories we can't yet interpret, hinting at processes invisible beneath the dust, inviting us deeper into mysteries that Mars seems determined to preserve for as long as possible, releasing just enough information to keep us interested, but never enough to satisfy playing the long game with investigators who have only just arrived and who are still learning how to ask the right questions, still developing the tools needed to hear what Mars has been trying to tell us all along: that the boundary between living and dead is softer than we imagined, that chemistry and biology blend into each other in ways we're only beginning to appreciate, that a world can be mostly dead, but partly alive, dormant, but not finished, silent, but still speaking to those patient enough to listen. Every extinction event writes its signature in stone. Geologists read these signatures the way historians read ancient texts, layers of sediment telling stories of what ended, what survived, what changed forever. On Earth, we've identified 5 major mass extinctions, moments when more than 70% of species disappeared within geologically brief periods. Each one left evidence iridium layers from asteroid impacts, carbon isotope shifts, from volcanic eruptions, oxygen depletion, markers from ocean anoxia. But Earth's extinctions were temporary. Life recovered, evolved, filled the empty niches. Mars experienced something different, a planetary extinction not of species but of habitability itself, a transformation so complete that recovery became impossible. And the evidence of what killed Mars is written across its entire surface, visible to anyone who knows how to read planetary death certificates. We should be reading it very carefully, because the processes that destroyed Mars's biosphere are the same processes that could, given enough time or carelessness, destroy ours. Mars died slowly, which somehow makes it worse. A catastrophic death asteroid impact, stellar explosion, sudden atmospheric loss would have been dramatic but quick. Mars's death took hundreds of millions of years, long enough for any organisms that existed to watch their world gradually become uninhabitable, long enough for adaptation to fail, for evolutionary solutions to run out, for the boundary conditions of survival to tighten year by year until nothing could meet them anymore. The cause was losing its magnetic field, and the consequence was losing everything else. Here's how it happened and why it matters to us. 4 billion years ago, Mars had a magnetic field comparable to Earth's. We know this from orbital magnetometer data collected by the Mars Global Surveyor, which detected strong magnetic signatures in ancient crustal rocks, especially in the southern highlands. These rocks formed when Mars still had an active dynamo, a liquid iron core convecting rapidly enough to generate a planet-wide magnetic field. The field served the same function as Earth's field does, deflecting solar wind, protecting the atmosphere from being stripped away by charged particles streaming from the sun. With that protection, Mars's atmosphere could remain, thick pressure could stay high enough for liquid water to exist on the surface, and climate could stabilize into conditions potentially suitable for life. Mars was habitable not hypothetically, but actually with all the physical requirements met. Then about 4.1 billion years ago, the magnetic field started weakening. We can date this by examining the magnetization of rocks of different ages. Older rocks are strongly magnetized, younger rocks less so until about 3.7 billion years ago when magnetization drops to near zero. The field didn't shut off instantly. It faded over hundreds of millions of years, gradually losing strength until it could no longer provide meaningful protection against solar wind. Why did it fail? Because Mars is small, 11% of Earth's mass, half Earth's diameter. A smaller planet has less internal heat, and its core cools faster. When the core cooled below the temperature needed to maintain vigorous convection, the dynamo weakened. Eventually, convection patterns change from organized flow, which generates coherent magnetic fields, to turbulent chaotic motion that produces no net field. The core is still liquid today, as InSight confirmed, but it's not convecting fast enough or coherently enough to generate a protective magnetic field. The shield failed. Mars stood exposed. Without magnetic protection, solar wind began stripping Mars's atmosphere directly. The process is called atmospheric sputtering. Charged particles from the sun, mostly protons and electrons traveling at hundreds of kilometers per second, hit the upper atmosphere, transferring energy to atmospheric molecules. If a molecule gains enough energy to exceed Mars's escape velocity, it leaves the planet permanently flying off into space. On Earth, our magnetic field deflects most solar wind before it reaches the atmosphere. So sputtering occurs only at the poles, where field lines funnel particles down. Mars had no such protection. Solar wind hit the entire dayside atmosphere. Everywhere the sun shone, stripping atoms and molecules continuously. The process was gradual. Mars didn't lose its atmosphere overnight. But over tens of millions of years, the accumulation became significant. Over hundreds of millions of years, it became catastrophic. The MAVEN spacecraft, Mars Atmosphere and Volatile Evolution. Mission arrived at Mars in 2014 specifically to study atmospheric loss. It carries instruments that measure the composition and velocity of atoms, escaping from the upper atmosphere, tracking where they go and how fast they leave. MAVEN's data showed that Mars currently loses about 100 grams of atmosphere per second to space. That sounds small until you calculate the accumulation. 100 grams per second equals 3.15 tons per year. 3.15 million tons per 1,000 years. 3.15 billion tons per million years. Over the 4 billion years since the magnetic field failed, Mars has lost a significant fraction of its original atmosphere, possibly more than what's there now, meaning Mars's ancient atmosphere might have been tens or hundreds of times thicker than the current whisper-thin envelope. The loss wasn't uniform. Lighter elements like hydrogen and helium escape fastest. Oxygen was split from water molecules by ultraviolet light and escaped as atomic oxygen. Carbon dioxide remained longest because it's heavy, but even CO2 gradually sputtered away. Nitrogen, crucial for biology, was lost almost completely. Mars's atmosphere today is less than 2% nitrogen compared to Earth's 78%. The composition changed as the pressure dropped, skewing toward heavier molecules that couldn't escape as easily. As atmospheric pressure decreased, surface water became unstable. Liquid water requires sufficient atmospheric pressure to prevent immediate boiling or freezing. On Earth, water is stable at sea level because atmospheric pressure is about 101 kilopascals. On Mars today, average surface pressure is about 600 pascals, less than 1% of Earth's well below the triple point of water. At such low pressure, liquid water cannot exist, except briefly as brine at high salt concentrations. And even then, only during the warmest times of day, in the warmest seasons. Mars crossed below the liquid water threshold sometime between 3.5 and 3 billion years ago, as best we can determine from geological evidence. Lakes began evaporating faster than they filled. Rivers stopped flowing except during brief catastrophic floods from underground ice melt. The ocean, if it existed, which seems increasingly likely, evaporated over millions of years, its water molecules dissociating in the upper atmosphere and escaping to space, leaving behind dried lake beds, ancient shorelines, and salt deposits marking where waves once crashed against coastal rocks. Temperature followed atmospheric pressure downward. A thick atmosphere creates greenhouse warming by trapping infrared radiation emitted from the surface. Mars's early atmosphere, rich in CO2 and possibly methane, likely provided enough greenhouse effect to keep surface temperatures above freezing, despite Mars receiving only 43% as much sunlight as Earth. As the atmosphere thinned, greenhouse warming decreased, temperatures dropped. The climate shifted from relatively warm and wet to cold and dry, then to the frozen desert we see today, where summer afternoon temperatures might reach 20 degrees Celsius at the equator, but nighttime temperatures drop to minus 100 degrees, and winter polar regions reach minus 140 degrees. Cold enough to freeze carbon dioxide out of the air, creating dry ice caps that sublimate back to gas each spring. What could Mars have done to prevent this nothing? It's not a matter of policy or engineering. Mars's size determined its fate. A small planet cools, quickly loses its magnetic field, and becomes vulnerable to atmospheric stripping. The trajectory was set at formation, locked into the physics of planetary cooling and magnetic field generation. Mars had perhaps 500 million years of true habitability before conditions began deteriorating noticeably, and another billion years of gradual decline before becoming the frozen desert we observe now. If life emerged during the habitable period, it had 1 billion years to adapt to worsening conditions, to move underground, to find refuges where water persisted. That's not nothing. 1 billion years is enough time for significant evolution. But eventually, the surface became completely uninhabitable. Any life that survived would have retreated to the subsurface, permanently isolated in aquifers and cave systems, separated from the surface biosphere that had died. Now, let's talk about Earth. We have a magnetic field generated by our larger, hotter core convecting vigorously enough to maintain a strong dynamo. Our field protects our atmosphere from significant sputtering, allowing us to maintain thick atmosphere and liquid surface water, despite receiving solar wind comparable to what Mars experiences. We're safe, right? For now, yes, Earth's core will remain hot enough to drive convection for billions of years, probably another 5 billion years, before it cools sufficiently for the magnetic field to weaken significantly. We have time, but we should understand that what we have is not permanent. Earth's magnetic field has reversed many times. In the past, the north and south magnetic poles flipping positions, and during reversals, the field weakens to perhaps 10 or 20% of its normal strength for thousands of years. During those periods, atmospheric sputtering increases, though not enough to cause dramatic atmospheric loss over such brief timescales. And field reversals are temporary. The field returns to full strength, eventually restoring protection. But they serve as reminders that our magnetic shield is dynamic, not static, and that we're dependent on processes deep inside the planet that we can't control or influence. There's a more immediate lesson from Mars, though, about atmospheric composition and climate stability. Mars didn't just lose atmospheric mass, it lost atmospheric composition, specifically the gases that provided greenhouse warming. When those gases were stripped away, the climate collapsed. Earth faces a related problem, though from the opposite direction. We're adding greenhouse gases, carbon dioxide from fossil fuels, methane from agriculture and industry, increasing the atmospheric concentration of molecules that trap heat. We're not at risk of losing our atmosphere to space. We're at risk of changing its composition so much that climate shifts beyond the range our civilization is adapted to, causing disruptions to agriculture, sea level, weather patterns, ecosystems. Mars teaches us that atmospheric composition matters profoundly, that small changes in trace gases can drive large climate shifts, that once certain thresholds are crossed, feedback loops can accelerate changes beyond what initial forcing would suggest. Consider what happened to Mars's water. As the atmosphere thinned and temperatures dropped, water began freezing into polar ice and permafrost. But frozen water reflects sunlight more effectively than liquid water, increasing planetary albedo, the fraction of sunlight reflected rather than absorbed. Higher albedo means less solar heating, which causes more freezing, which increases albedo, further creating a runaway feedback loop called ice albedo. Feedback. Mars spiraled into a frozen state partly because of this feedback, and once frozen, reversing the process became nearly impossible. Earth has similar feedback mechanisms. Arctic sea ice, for example, reflects sunlight. As climate warms and sea ice melts, darker ocean water is exposed, absorbing more sunlight, causing more warming, melting more ice. The feedback accelerates change beyond what greenhouse gas increases alone would cause. We're watching this happen in real time. Arctic sea ice extent has declined about 13% per decade since satellite monitoring began in 1979. The feedback is active. The system is responding. Mars also demonstrates what happens when a planet loses its water cycle. On Earth, water evaporates from oceans, forms, clouds precipitates as rain, or snow runs through rivers back to the ocean. This cycle distributes heat, moderates temperature, weathers, rock, transports nutrients, and maintains surface conditions suitable for life. Mars had a water cycle once. When it stopped, when pressure dropped too low for liquid water and temperatures fell too far for significant evaporation, the planet's surface became static, frozen in time, with no mechanism to redistribute resources or moderate conditions. Dust storms became the main transport process, moving fine particles around, but not providing the chemical and thermal regulation that water provides. The surface became more hostile with each passing million years, trending towards sterility. Earth's water cycle is robust, driven by vast oceans and thick atmosphere. But regional water cycles can collapse. The Sahara Desert was green 6,000 years ago, lakes, rivers, vegetation, supported by monsoon rainfall. When Earth's axial tilt changed slightly, shifting the position of the intertropical convergence zone, rainfall patterns changed. The region dried out. Vegetation died. Soil blew away. The light-colored sand that replaced dark vegetation increased albedo, reducing solar heating, decreasing convection, suppressing the formation of rain clouds. The feedback locked the region into desert conditions that persist today. A regional water cycle collapsed, and the landscape transformed into something resembling Martian terrain, sand, rock, rare and precious water. What happens to Mars at a planetary scale can happen to Earth regionally, and what happens regionally can, under certain conditions, spread globally. There's also a lesson about oxygen. Mars's atmosphere contains almost no free oxygen, about 0.15%, compared to Earth's 21%. Oxygen on Earth is maintained by photosynthesis, with plants and phytoplankton continuously replenishing oxygen that reacts with organic matter and minerals. If photosynthesis stopped, if plant life went extinct, Earth's atmospheric oxygen would decline over thousands to millions of years as oxidation reactions consumed it. The atmosphere wouldn't lose pressure immediately, but it would lose breathability. Complex life that depends on oxygen would go extinct. Mars might have had oxygen once if it had photosynthetic organisms. When those organisms died or went extinct, oxygen levels would have dropped, removed by reactions with surface minerals like iron. The red color of Mars's surface comes from iron oxide rust, indicating oxygen reacted with iron extensively. Any oxygen that was present got locked into rock, making it unavailable for biology. Perhaps the most sobering lesson from Mars is about irreversibility. Once certain changes occur, magnetic field loss, atmospheric escape, water loss, temperature drop, reversing them becomes extraordinarily difficult or impossible with natural processes. Mars couldn't restart its magnetic field. It couldn't recapture lost atmosphere from space. It couldn't rewarm without greenhouse gases it no longer possessed. The planet crossed thresholds beyond which recovery was impossible, locked into a trajectory toward its current frozen state. Earth hasn't crossed such thresholds, and our timescales for natural change are much longer than human lifespans or civilizational timescales. But the principle applies. Some changes, once initiated, become self-reinforcing and difficult to reverse. If Greenland's ice sheet melts completely, which becomes more likely with each degree of warming, sea level rises about 7 meters globally. The water absorbs more solar heat than ice did. Ocean circulation patterns change. Weather patterns shift. The climate finds a new equilibrium state that might persist for thousands of years long, beyond any human capacity to restore what was lost. Mars is a cautionary tale written in geology. It shows us what happens when a planet loses the physical conditions that allow life to exist at the surface. It shows us that habitability is not guaranteed, that it depends on factors beyond any biosphere's control, that planets can die. And when they do, the death is usually permanent on timescales that matter to living things. We're not Mars, we're larger. We have a protective magnetic field. We have robust oceans and a thick atmosphere. But we're still vulnerable to composition changes in that atmosphere, to shifts in climate that push conditions outside the range we've adapted to feedback loops that accelerate changes beyond our capacity to mitigate them. Mars couldn't prevent what happened to it. We can prevent what might happen to us but only if we pay attention to the warnings written in another world's rocks, only if we take seriously the lessons that planetary death teaches about the fragility of the conditions that allow life to flourish. Looking at Mars is looking in a mirror that shows not what we are, but what we could become if we're not careful. A world with water that lost its water. A world with atmosphere that lost its atmosphere. A world that might have hosted life but became a tomb. The transformation wasn't quick or dramatic. It was gradual, incremental each year, slightly worse than the last, each decade crossing small thresholds that accumulated into catastrophic change. By the time the damage was irreversible, it had been happening for so long that it seemed normal, inevitable, just the way things were. That pattern slow decline, normalized over time until recovery becomes impossible, is what we should fear most. Not dramatic collapse, but gradual erosion of the conditions we depend on each generation, adapting to slightly worse circumstances until one day we realize we've crossed a line we can't uncross, and the world we took for granted has become something else entirely. Something less habitable, less forgiving, less alive. Mars isn't just a scientific curiosity or an exploration target. It's a memorial to what happens when protective systems fail and a planet loses the delicate balance that sustains life. We should visit that memorial often. We should read the inscriptions carefully. We should make sure the story written there never becomes our own. Because unlike Mars, we have the knowledge and tools to change our trajectory, to maintain the systems that keep Earth habitable, to avoid repeating on our own world. The transformation that turned Mars from a living planet into a beautiful, silent, empty museum of what used to be possible frozen in time, waiting for someone to arrive and recognize what was lost, and perhaps to understand why. There's a photograph taken by the Curiosity rover in 2014 that I think about often. It's looking back at its own tracks and the dust-twin parallel lines stretching toward the horizon, disappearing into the salmon-colored haze where land meets sky. The tracks are the only evidence of motion in the entire frame. Everything else is still patient waiting. And there's something profound in that image, something about persistence and presence, about the fact that we're there at all, that a machine built by human hands is crossing a desert on another world, leaving footprints that might last 1,000,000 years in the absence of wind and rain to erase them. We're writing our story on Mars now, not just reading the one already written. We're becoming part of its history, adding our chapter to a narrative that began 4.6 billion years ago, when a cloud of dust collapsed under its own gravity and began spinning, heating, condensing into planets. That dust cloud is where everything comes from. Earth, Mars, you, me, the device you're listening on, the air in your lungs. We're made of the same material as Mars, assembled from the same atoms, born from the same stellar deaths that scattered heavy elements across the galaxy. When a massive star exhausts its fuel and explodes as a supernova, it forges elements heavier than iron in the intense heat and pressure of collapsed gold, uranium, platinum, all the atoms that weren't created in the steady fusion of normal stellar burning. Those atoms disperse into space, mixing with hydrogen and helium, left over from the Big Bang, floating in vast clouds until gravity draws them together again. Our solar system formed from one such cloud about 4.567 billion years ago. The sun ignited at the center, planets condensed from the remaining disk of dust and gas. Mars formed at 1.5 astronomical units from the sun. Earth formed at 1.0 astronomical units. The difference was location and timing, nothing more meaningful than that. We could have been Mars. Mars could have been us. The initial conditions varied only slightly, but those slight variations determined everything that followed. For the first billion years, Mars and Earth were similar. Both had thick atmospheres, surface water, volcanic activity impacts from the late heavy bombardment raining debris onto both worlds. Both were hellish, violent, gradually settling into calmer states as the solar system cleaned itself of construction debris. Life emerged on Earth. During this period, we have fossil evidence of microbes dating back 3.5 billion years. and chemical evidence suggesting life might be even older, perhaps 3.8 or 4 billion years old. Did life emerge on Mars during the same window? We don't know yet, but the conditions were comparable. The chemistry was present, the energy was available, the time was sufficient. If life is a natural consequence of chemistry under the right conditions, then Mars should have had life. Whether it did or not is the question that drives every rover, every orbital mission, every instrument we point at the red planet. And here's what strikes me: whether Mars had life or not, the story is meaningful either way. If Mars had life and lost it, then we're looking at a dead biosphere, an entire domain of biology that evolved adapted and ultimately failed when conditions deteriorated beyond any organism's capacity to survive. That makes Mars the largest cemetery in the solar system, a planetary tomb containing the remains of billions or trillions of organisms that lived and died in environments we're only now learning to reconstruct. Finding fossil evidence would answer one of humanity's deepest questions. Are we alone with a definitive no? Life emerged at least twice in one solar system, suggesting it's probably common throughout the universe. Every star with planets probably hosts life somewhere in some form, adapted to local conditions. The cosmos would be full of biology, most of it microbial and simple, but alive, nonetheless processing energy and reproducing and evolving. We'd be part of a living universe, one expression among countless others of what matter does when given energy and time. But if Mars never had life, if it was habitable but remained sterile, then that's equally profound. It would mean habitability alone isn't sufficient, that life requires not just the right chemistry and environment, but also some additional factor we don't understand yet. Perhaps a specific sequence of chemical reactions that's improbable despite being possible. Perhaps conditions must persist for longer than Mars's habitable period allowed. Perhaps life is genuinely rare, a fluke that happened on Earth through extraordinary luck and didn't happen on Mars despite similar circumstances. That would make Earth special, not in the sense of being cosmically important, but in the sense of being unusual, a rare island of biology in an ocean of sterile chemistry. It would mean when we look at the night sky, most of what we see is empty, lifeless, just physics and chemistry proceeding without the complication of organisms. And it would mean we're alone, at least in our stellar neighborhood, possibly in our galaxy, perhaps in the entire observable universe. That loneliness would be both terrifying and precious terrifying, because it means consciousness is fragile and might not survive our own mistakes precious, because it means we're responsible for the only instance of the universe becoming aware of itself, asking questions about its own nature, creating art and science and meaning in the face of cosmic indifference. Either answer changes how we see ourselves. Either answer matters enormously, and Mars holds that answer written in rocks and soil samples we haven't collected yet, in subsurface aquifers we haven't reached yet, in mineral deposits we haven't analyzed carefully enough yet. The answer exists. We just need to ask the right questions and look in the right places. That's why we keep going back, keep sending more sophisticated instruments, keep pushing technology toward the capability to drill deep and sample broadly and analyze precisely. We're not exploring Mars because it's there. We're exploring Mars because we're there, because consciousness demands understanding, because humans are the part of the universe that looks at the rest of the universe and wants to know what it all means. And maybe that's the deepest connection between us and Mars. We're both trying to understand something larger than ourselves. Mars is trying to tell us its story, encoded in geology and chemistry, in the ratios of isotopes and the structure of minerals, in the shapes of valleys and the chemistry of brines. We're trying to read that story using robots and spectrometers and seismometers as our translators, slowly learning the language of planetary death and possible life. It's a conversation across time and space between a world that lived and changed and possibly hosted biology and a species that evolved on a neighboring world and developed enough technology to reach across the gulf and ask questions. That conversation is still early. We've only been listening for 60 years, only landing for 50 years. only deploying sophisticated instruments for 20 years. Mars has been trying to tell us its story for 4 billion years. We're just now learning to understand. What happens next depends partly on us. We can continue exploring, improving our tools, drilling deeper, sampling more sites, bringing materials back to Earth for detailed analysis. We can send humans eventually establishing a permanent presence that allows hands-on investigation impossible for robots. We can potentially terraform Mars over thousands of years, thickening the atmosphere, warming the surface, coaxing water back to habitability, creating a second home for Earth life. Or we can decide Mars is best left, as it is a natural laboratory, a pristine record of planetary evolution, a memorial to what was lost, and a warning about what we could lose. Those choices haven't been made yet. The conversation about what we should do with Mars is still developing, still contested, still open to multiple futures. But whatever we decide, Mars will continue its slow transformation with or without us. The planet is still processing, still changing, just at rates imperceptible to human observation. Marsquakes still rumble through the interior. Dust storms still redistribute surface materials. Polar caps still sublimate and refreeze with seasons. Methane still appears and disappears according to patterns we don't understand. The planet is active, dynamic, alive in the geological sense, even if not the biological sense. It has agency in its own story, preferences encoded in physics and chemistry trajectories that will continue regardless of human interest. We're observers and participants adding ourselves to Mars's narrative, but not replacing what was already there. The planet has its own arc, its own trajectory, its own destiny. We're just visiting, paying attention, trying to learn what 4 billion years of planetary evolution can teach us before we have to apply those lessons to our own world's future. There's a concept in astronomy called the cosmic perspective, the recognition that everything we care about, everything we fight over, every human concern and worry exists on one small planet, orbiting an ordinary star in an unremarkable galaxy containing 200 billion other stars with their own planetary systems. From that perspective, human affairs seem trivial, insignificant, barely worth noticing. But there's another way to see it. We're not insignificant. We're the universe figuring itself out. Matter organized into structures complex enough to wonder about their own existence. Every human thought, every scientific discovery, every moment of consciousness is the cosmos, experiencing itself, becoming briefly aware before that awareness disperses back into unconscious matter. Mars can't think about itself. It can't wonder about its own history or regret what it lost. We can do those things. We can look at Mars and see both what it was and what it became. And we can use that knowledge to avoid similar fates, to maintain the conditions that allow thought to continue, consciousness to persist, understanding to deepen. That's not insignificant. That's the opposite of insignificant. That's the universe's only defense against entropy and meaninglessness, pockets of complexity that resist dissolution, that maintain order locally, even as disorder increases globally, that create beauty and understanding and purpose in the face of physics, that tends towards simplicity and heat death. Earth is one such pocket. Life on Earth is an anomaly, an improbable configuration of matter that maintains itself far from equilibrium, using energy from the sun to build structure and resist decay. Consciousness is an anomaly within that anomaly, emerging from biological complexity to create art and science, meaning and morality. And now that consciousness is reaching beyond its home planet, extending sensors and cameras to other worlds, reading histories written in alien geology, finding connections across the solar system, recognizing kinship with a frozen desert 100 million miles away, because it too is made of stardust, shaped by the same physical laws, following the same rules of chemistry and thermodynamics that govern everything else. When I look at Mars now, I don't see a dead planet. I see a relative, a sibling world born from the same cloud, shaped by the same forces following a different path because of size and location and chance. I see a warning about fragility and a reminder about resilience. I see a question we're still trying to answer about whether life is common or rare, whether consciousness is abundant or precious. I see the past Earth could have had if conditions were slightly different, and the future Earth might face if we're not careful. I see beauty in the desolation, complexity, and the emptiness, meaning in the silence. Mars isn't speaking loudly or clearly. It whispers leaves, hints makes us work for understanding. But every piece of data returned, every image transmitted, every sample analyzed, brings us closer to comprehension, closer to knowing what happened there and why, closer to understanding our own world by comparison. And ultimately, studying Mars is studying ourselves. Not because Mars is like Earth, it isn't anymore though, it was once. But because understanding planetary evolution helps us understand planetary death. And understanding planetary death helps us avoid it. Mars is our teacher, our example, our cautionary tale. It shows us what happens when protective systems fail, when atmospheres thin, when water disappears, when magnetic fields shut down. It shows us that habitability is not permanent, that conditions we take for granted can change, that planets are not stable platforms, but dynamic systems that evolve over billions of years, sometimes toward greater habitability, sometimes away from it. We're lucky to live during Earth's habitable period, lucky that our magnetic field still functions, that our atmosphere remains thick, that our water cycle continues. That luck is not guaranteed to last forever. The sun is slowly brightening, increasing in luminosity by about 10% per billion years, which means Earth will eventually enter a runaway greenhouse phase where oceans evaporate and the planet becomes uninhabitable probably within a billion years. Not soon by human standards, but not infinitely far in the future either. Our time on this world is limited. What we do with that time matters. Mars teaches us gratitude for what we have: atmosphere, water, magnetic protection, climate stability. It teaches us caution about changing systems we don't fully understand. It teaches us humility about our place in cosmic time, reminding us that civilizations are brief and planets are long, that what we build will vanish, but what we learn might persist if we share it. If we pass knowledge forward, if we maintain the continuity of understanding across generations. Most of all, Mars teaches us connection, that we're not separate from the cosmos, but part of it, made of it, embedded in its history, following its laws, participating in its evolution. We are the way the universe knows itself. Mars is the way the universe shows us what we might lose if we're careless. Together, they form a story about what's possible and what's fragile, what endures and what transforms, what lives and what dies, and what might live again if conditions change. So, rest now and let these thoughts settle gently. We've traveled far tonight, from ancient observations to modern rovers, from dead oceans to hidden lakes, from methane mysteries to planetary warnings. We've listened to Mars whisper its secrets, watched it reveal its history, learned what it's trying to teach us. The journey continues. The story isn't finished. Every mission brings new discoveries, new questions, new mysteries that require patience and persistence to solve. And you've been here for all of it, listening, learning, letting curiosity guide you through this quiet exploration of another world. Thank you for staying with this story. Thank you for caring about a planet that can't thank you back, that doesn't know we're watching, that continues its slow transformation regardless of human attention. Your curiosity matters. Your interest drives exploration, funds, missions, keeps the conversation going about what we should do with the knowledge we're gaining. You're part of this story, now connected to every rover that drives across Martian dust, every instrument that measures atmospheric gases, every scientist who analyzes data, trying to understand what it all means. The next chapter is already being written, samples being collected by Perseverance, ready for eventual return to Earth, drilling missions being designed to reach subsurface water, human missions being planned for the 2030s. Mars keeps calling us back, keeps offering new mysteries, keeps suggesting that maybe we'll find what we've been looking for all along. Evidence of life beyond Earth, proof that we're not alone. Confirmation that the universe is richer and stranger and more alive than we dared hope. Whether we find that evidence or not, the search itself is meaningful. The questions we ask reveal who we are. The tools we build demonstrate what we value. The knowledge we gain shapes what we become. Sleep well, dream gently, and when you wake, look up at the sky. If you see a red star that doesn't twinkle, that holds steady while others dance, know that we're there now, walking on that distant world, reading its history, searching for answers, continuing the conversation that ancient observers started 4,000 years ago, when they first noticed a light that moved differently than the others and wondered what it meant. The answer is still arriving, traveling toward us at the speed of light, carried in data packets and rover transmissions, waiting for patient minds to decode and interpret and understand. And there are more stories waiting to be told, more journeys to take together through space and time, and the quiet science of worlds beyond our own. Until then, rest in the knowledge that the universe is vast and beautiful and full of mysteries worth exploring, and that somewhere in that vastness, a small machine built by curious primates is driving across red dust under a salmon sky, looking for signs of life, carrying humanity's questions to a world that might finally be ready to answer them. Good night.